Okay, Justin, if you could go back to the first slide. Okay, perfect. Hi, good morning, everybody. Welcome. This is the final University Coalition for Fossil Energy Research Annual Technical Review meeting. My name is Omer Bakshi, and I am the DOE Project Officer for UCFER here at NETL. We're in the home stretch, so I'm pretty excited to see what kind of technical updates we have from our presenters today. Before we get started, I want to let you guys know that this meeting is being recorded and that the recording will be made available to anyone interested after the meeting. And I do have to read some language. So this meeting is considered to be an open to the public meeting. All information shared at this meeting has been cleared for public presentation and has already been published in the public domain and will be made available after the meeting. Discussions and information sharing during or in relation to this meeting should not include material that is considered official use only, proprietary, sensitive, restricted, or protected in any way. Please err on the side of caution and avoid discussing materials that you think could meet these criteria. Now that that is out of the way, before I go into the nuts and bolts about the logistics of this meeting, I will pass it off to Dr. Brian Anderson for some brief opening remarks. So Brian, the floor is yours.
Well, Omer, thank you very much, and to the whole University Coalition for Fossil Energy Research team. Thanks for all of your hard work and innovations over the past few years, and in particular the involvement of the university researchers with our in-house R&D partners within the Research and Innovation Center. I hope that one of the major outcomes has been the opportunity presenting itself for collaboration into the future, and certainly it's right now. Many of you, if not all of you, should be aware that the country as a whole is on a pretty aggressive pathway toward decarbonization, and we here at NETL are really, in fact, critical. The technologies that we're developing with university partners like you is going to be needed in order to achieve the goals of the administration. So I'm really happy that we're meeting here to share some of the updates of these cutting edge research projects that are being conducted by the UCFER research partners. And today I know we're going to talk about carbon management technologies. We're going to talk about point source carbon capture, integrated carbon management, hydrogen fuel production and delivery, emissions quantification, and recovery of rare earth elements. And these topics are very, very important to the pathway toward decarbonization. And so I'm happy to have this collection of top university research talent here, because there are some significant energy challenges facing us in order to get to the administration's goals of cutting our emissions in half in the next 3 years, 2 months, and 26 days, cutting our emissions to net zero across the entire economy by 2050, and decarbonizing the power sector by 2035. These are pretty aggressive goals, and they require very innovative solutions in order to get there, while simultaneously ensuring that we have resilient, reliable, and affordable energy, and doing it in a way that is equitable through the transition. I often talk about this energy transition being a very path-dependent transition, and what I mean by that is that we know what the end goals are. I just stated them: net zero carbon across the economy by 2050. And when we think of the way to get there, there are a number of different paths. Not all of those paths result in an energy transition that is equitable to communities that can be left behind in the transition. It's not always equitable in terms of the cost of energy and the reliability and affordability. And so when we think of the full ensemble of pathways to get to a net zero economy by 2050, what is really important is that we have a very robust set of technologies that are ready to start plugging into that transition. And the ones that you're working on in these areas, I think, are absolutely critical, particularly when we think about the decarbonization challenge. You can roughly break it into into quarters in terms of our emissions today. Our emissions today are roughly 1/4 electricity, 1/4 industrial sources, 1/4 transportation. Now, of course, that transportation has overtaken the electricity sector in terms of emitting more, so it's actually 27%. And then the final quarter of our emissions in the United States are commercial, residential, and agriculture together. And when we think about those different segments and the pathways to get there, it's going to require a lot of different technologies to be not only commercialized but still innovated. The new innovations in how to do large-scale decarbonization for transportation, certainly electrification, but then also advances in other low-carbon sources. And then when we think of the extremely hard to decarbonize part of the transportation sector, particularly aviation, we need circular carbon, zero carbon liquid hydrocarbons, and in fact are probably going to be the best pathway to fully decarbonizing aviation. And then obviously our work that at NETL dates back 25, close to 30 years in point source carbon capture beyond electricity will need to be deployed in the very near future in a wide variety of scales. It can be in the large scale carbon capture for point source power, but then when we think of the industrial sector and the needs across many different hard to decarbonize segments of the industrial sector, these technologies are absolutely very important. So we need lots of research, development, demonstration, deployment of these decarbonization technologies to help drive that energy transition to get us where we need to be by 2050. And so, personally, my history, many of you may know, it wasn't that long ago. I was a UCFER member and a very proud member of the UCFER. And today, looking back at the innovations that you're working on, very proud of the UCFER portfolio. And so to dig a little deeper, and certainly there's lots of time today to do that into the different technology areas, these priority areas, as I've mentioned, in integrated carbon management, goes a step beyond the large-scale centralized power generation of today and of the past, because that decarbonization pathway for the electricity sector is going to end up resulting in wide variation of intermittent renewables, energy storage, electricity storage, even thermal energy, chemical energy storage, and electricity storage, and new innovations in those point sources for firm power. We see it in the nuclear power sector, the move towards small modular nuclear reactors, advanced reactors that have even integrated combined heat and power options for some of the new advanced nuclear. That is a revisit of the nuclear reactors that were developed in the 1950s and 60s. And so that's just one example. When we're now looking forward to that firm power production, it's going to be done in a much more integrated way, where it's combined heat and power, it's power production, it's co-production of things like hydrogen and chemical fuels using direct air capture. We're moving much more toward integrated energy systems to be able to maintain reliable, resilient, affordable power with much deeper renewables penetration. That requires the point source carbon capture technologies to drive down the costs, drive down the cost of capture, drive down the cost of compression and transmission, and then ultimately reducing the cost and risk of permanent storage in the subsurface. When we think of, again, going back to the quarter by quarter, the contributions of our CO2 emissions in our economy, when we start to look at the options for decarbonizing the industrial sector, obviously hydrogen and other no carbon energy carriers like ammonia really come to the forefront. And so there's a lot of interest globally, as many of you may be aware, in using ammonia as that hydrogen energy carrier, because it can be distributed as a liquid and much more amenable to putting on large ships across the ocean. But getting and producing the hydrogen at low cost, we need all of the options. And so the work in hydrogen production and then transportation, distribution, and final use is of tremendous importance. And so I encourage those who are working in this space, keep at it. We need advances in the technologies for clean hydrogen production, and all of the technologies, including the material science in the midstream and downstream use of hydrogen. But then when we move to a hydrogen economy, it is absolutely critical and vital that we know that the upstream production of natural gas, which much of the hydrogen will be produced from natural gas, either steam methane reforming or methane pyrolysis, we need to ensure that the upstream is leak-free. And so our work in emissions quantification and reduction is absolutely paramount as we the globe, move to the low energy economy. And many of our trading partners are interested in the embodied carbon footprint of any hydrogen or liquefied natural gas that we produce here in the US. And then that whole energy transition is, we'll need to leverage our work in rare earths and critical elements and critical minerals for sure. The demand will only increase, and so ensuring that we have robust supply chains that don't run through single supply chain bottlenecks, and ensuring that those critical minerals and rare earth elements have sustainable practices built into their production, because when we consider the full life cycle impacts, the full economic and environmental impacts of energy production and energy systems manufacturing, it again is very critical that we develop new environmentally sustainable practices for the production of rare earth elements and critical minerals. And so highlighting a few of the context of many of the projects that will be presented today, I could not be more excited about the enthusiasm and the interest from academic partners, the students who are working on these projects, because achieving these carbon reduction goals over the coming decades, the students that are working on these projects are the future workforce. And you, if you're on the line here as a student, you're the ones who are going to get us there. And so thanks for your hard work and your dedication in this space, and really look forward to hearing the results as the day goes on. So Omer, thank you for giving me a chance to come in and offer a few words, and I'll hand it back to you. And again, thanks to the entire team, NETL team and the Penn State team for all the work that they've done in this UCFER program over the years. So thanks again.
Thank you, Brian. Really appreciate you being so gracious with your time and being able to offer such good opening remarks. Hopefully you'll be able to stick around for as many of these presentations as your schedule will allow. If not, you can always watch the recording afterwards. So moving on, you should all be able to see, well, you should all have copies of the agenda. If you don't already have a copy of it, there's a side panel with a handouts tab that you can expand and use to open the meeting agenda for today. The presentations can be found on the UCFER website. That is the URL if you would like to screenshot it, but I think the URL is also available on the agenda if you download it. If you were to go through the agenda, you'll see that we have a morning session, lunch, an afternoon session, and an afternoon session that is split with a break. There will be 20 minutes per presentation. We will message you time warnings for 5 minutes and 1 minute. Hopefully we'll be able to stay on time for today's meeting. And we ask that before we head into any of our breaks, that includes the lunch or the afternoon break, If you are slated to present in the following session, please try to stay on so that we can quickly check your mic. If you're not on, then we'll check about a couple minutes before we resume to see if your mic is working. So as for the Q&A, we ask that you send in typed questions into the question box that should be on the same side panel that the handouts tab is in. If you are unable to access the question box, then you can submit your question to the chat box and we will record it. If the need arises, we will unmute your microphone so that you can speak and provide more context to some of your questions if it's easier to verbalize. Now, moving on to the next slide. I just want to give some very important acknowledgements here. The UCFER staff at Penn State has been so crucial and so instrumental in making sure that all of the research accomplishments are captured, that all of the research subcontracts remain on track for completion. All of the administrative work that's this entire cooperative agreement requires has been handled so effectively and gracefully by the staff at Penn State. So I want to acknowledge the PI, Bruce Mueller, Elizabeth Wood, Jennifer Matthews, and Kelly Rhodes for all of their hard work. And hopefully, as we're in the home stretch, you guys will continue to perform as you've been doing. I look forward to working with you throughout the closeout process. And on the NETL side, I want to thank Lauren Timko, who's basically been my right hand in helping administer University Coalition. Lauren, you've done incredible work in helping me out, and I know you'll continue to do as good a job as you've been doing. I want to thank Karen Blaney for helping with the registration and helping us keep track of attendees and everything on the NETL side for getting this meeting approved. Justin Solly and Katie Moore, you guys are working very, very diligently in the background to make sure this webinar runs smoothly, and you've been doing that for the last 2 years. So I'd like to thank you both very much for all of your contributions to that end as well. So in case you haven't noticed, anyone who's presenting will only be speaking, and the slides will be controlled on the Penn State end. So if you do need your slides advanced, just simply say next slide. Because of some bandwidth issues, because this meeting is being recorded, there may be a delay. So if you notice that your slides have not advanced after giving the instruction to do so, just give it maybe a couple seconds, and then hopefully things won't be too slow. But there will likely be a lag, especially if there are animations or anything of the sort in your presentation. So this is practice time to use right now. If you want to submit a question to the question box, you may do so, or the chat box, whichever is available to you, and we will answer them as the meeting progresses. So in the interest of time, we will move on to the next item in our agenda, which is the State of the Coalition presentation by PI Bruce Miller. So once we get those up, Bruce, the floor will be yours.
Thank you. Okay, thank you, Elizabeth. Well, I want to start out by first welcoming, excuse me, all the attendees to today's meeting. And as you heard, all the presentations are up on our UCFER website. As was also mentioned, this is our last technical review meeting because, as you can see, this project ends in June, next June. Liz, next slide. One of the things I wanted to point out, and if you have been on the website already, you'll see I have 2 presentations up there. As you can see on the bottom of this, I have some supporting and extra slides because when I originally started out, I was going to really skip most of the background and organizational structure because originally I thought, everybody's already seen that, and I was going to try to leave time for other things. But I realized we have several people today who this is probably their first meeting. So I will have a brief discussion of our background and organizational structure. I'll discuss the research focus, funding, and status. The collaboration with NETL has been a major part of this project. I mean, those who submitted proposals will note that part of the review process and scoring process was that collaboration with NETL was a major item. The other thing we've been trying to do is determine the impact of this program. So there's several things that we have been monitoring, information we've been pulling out of quarterly reports and final reports and emails to the PIs. Then I'll discuss outreach activities, and we've started the final report, and I'll talk about that a little bit because this will be an almost 8-year program, and this final report's going to be massive. And then, of course, acknowledgements. Next slide. For those of you who are fairly new, UCFER was established in late 2015, and it was originally 9 universities. We added 7 more in 2017. And during this time, 1 university withdrew. But the overall goal for this program was to advance basic and applied energy research and to promote university and NETL collaboration for more efficient and more environmentally friendly utilization of fossil energy resources. And a major impact of this program is that this is a national university alliance with NETL. And details of our organizational structure and detailed operation can be found at this website because it also contains things like our bylaws and just how we were structured. Next slide, Liz. This image really just shows the wide geographical distribution of the universities that are part of the coalition. And what's really nice is they bring a wide variety of fossil energy expertise. Next slide. This is the organizational chart. This is, as you've heard, this is housed at Penn State. And so it's primarily being operated by a small group, which we call the operations management team. And what I probably should have had on here is there's a lot of people at Penn State who are also behind the scenes helping making this work. But there are 2 boards, or a technical advisory council, core competency advisory board. These 2 groups have a member from each university, and they assist the director in things like proposal review and directions of some of the funding, and works closely with an executive council. But all the research projects are focused around the 5 core competency areas that you see listed there. And of course, really, the base of this whole program are the faculty researchers at all of these universities. And again, there's more information on the details of all of this on our website. Next slide, please. This is a timeline of the program. You know, as we mentioned, we were notified of the project award in late 2015. We went through a definitization period, and so the project really started early 2016. And so you can see from this that the major activity is on UCFER was from like mid-2016 to early 2021. That was when all the work was done through the 6 rounds of solicitations for, with project selection, project starting. And what we'll do is a little later in the presentation, we'll revisit this active time period when I discuss some of the web activity that is going on. Next slide. The research funding through the 6 rounds of solicitations included 12 topic areas that are funded, maybe 13. I combined coal beneficiation and advanced coal processing. But for research, there was close to $17 million of funding available. We have received 259 proposals through these solicitations that were requesting $67 million. And in the end, 43 projects were awarded, although one did withdraw prior to starting. But you can see from this some of the big areas, and as Brian had mentioned, you can see carbon capture, carbon storage, carbon use and reuse. These were some of the biggest areas where funding was available. Next slide. What I just wanted to show here was just a summary of the proposals that were, number of proposals submitted, the amount of funding available, number of projects funded through the 6 rounds. Because I was just trying to get an idea of what the success rate was for the faculty who were submitting proposals. And you can see it varies from about 14 to 24% in the rounds, with a total of around 16% of a success rate. I'm not sure, if this was good or if this is typical. We have administered 3 other consortia over the years, and these numbers are somewhat similar, might be a little bit lower, but I think this was a good level of success in the program. Next slide, please. And this breaks us down a little bit more by technology line. And one thing I do want to point out, each of these technology lines also had some subtopic areas, and those you'll find listed in the supporting slides. It just got too busy, the slides. But you can see from this that carbon capture, storage, reuse, that's where most of the projects were funded. This was then followed by cross-cutting research and analysis, advanced combustion, and fuel cell technologies. But overall, it seems like a very nice mix of projects and project areas. Next slide, please. I have a couple slides here that summarize the round 5 and round 6 solicitations. The rounds 1 through 4, they're in the supporting slides because those projects are all completed. Now, there will be one round 4 project presented today because it's just recently was completed and the final report is in preparation. But you can see in round 5, this lists funding available, requested, how many proposals. And you can see we already have a couple of the projects have been completed. There are 4 in progress, and you will see presentations from 2 of those today under natural gas technologies and rare earth elements. Next slide. And in round 6, we had 7 projects funded. One did withdraw, and you'll see presentations from all of these projects, which include the cross-cutting research, advanced coal processing, and carbon capture. Next slide, please. So the status, as I mentioned, all rounds 1 through 4 projects have been completed, including the 2 completed projects in round 5. Of the 42 projects, 31 have been completed. There's 11 ongoing. Now, 5 of them will be done by the end of the year, and then the round 6 projects will be completed February of this coming year. Next slide. Well, we talked about NETL collaboration, but we were also trying to get university collaboration in this program. And so we did have universities collaborating on proposals. In the first 3 rounds, you can see 2 projects were funded out of 11 proposals. One was in advanced combustion, Penn State and Princeton, and both were in advanced combustion. And then one was Texas A&M with Princeton. Next slide. In the last 3 solicitations, there were 11 proposals again that had collaborations among the universities. and one was funded in carbon capture with Wyoming and Penn State. Next. Okay, and I know there was some discussion on this already, collaboration with NETL. As I mentioned, that this was a major requirement for all the funded projects, and these are some of the examples of the collaborative efforts. You know, there was NETL staff time, you know, to support the collaboration, internships at NETL, on-site testing and equipment usage, co-mentoring students, co-authoring journal articles and conference papers. There were several CRADAs, and I think I'll mention this in a little bit later too. The problem though, I think some of the on-site collaborations, they didn't pan out because of COVID. There were restrictions, and so I think there were some activities that were lost as a result of that. Next slide. As I mentioned earlier, we're really trying to take a look at the impact of this program. I mean, you know, essentially, along with the research results, what are some of the other metrics you could look at that would see if this overall program is successful? And as I mentioned earlier, I mean, one impact is this is the first National University Alliance in fossil energy research with a major collaboration with NETL. As of late September, there were 254 participants. As you can see listed here, we've had over 200 faculty and students that have been participating on the various projects. And as I mentioned earlier, university and university collaborations, about 8% of the proposals contain the collaborations, and about 7% of the funded projects had the collaborations. But you can see faculty, graduate and undergrad students, who have research staff, postdocs, visiting scholars, had some participation with non-coalition universities, as well as companies and national labs. Next slide. Well, excuse me, this is what we call products. And as earlier I mentioned CRADAs. Well, there were 10 that were executed or pending. I'm not sure exactly how many were implemented at NETL. But when you take a look at the products, what we have, the different ones we have listed here: conference papers, journal articles, patents, presentations, dissertations, and more. So far, we have listed here like 285 products. And of these, like 215 are papers, presentations, and posters. But we've also have non-coalition participants, which included 6 universities and 15 companies. And this included subcontractors, people providing cost share. Several of the projects had to have cost share, unpaid consultation, sample analysis, advisory board members, and providing materials for testing. Next slide, please. One of the things I wanted to also take a look at is where NETL was participating in papers, presentations, posters, journal articles. And this slide shows the papers, presentations, and posters. And of these 215, of the 215, 43 are conference papers, and 40 of the 43 conference papers, 8 of them, or 19%, contain NETL co-authors. And one of the things you'll note here, which would only make sense, is that most of these are from the early rounds, because the later rounds are, they're fairly new. But what I think is very telling, next slide, is that of the 45 journal articles to date, a third of them contain NETL co-authors. And so I think that is good. It shows some good collaboration between the faculty researchers and NETL. I think This is going to probably even get better as we go on. Now, again, you can see here definitely, journal articles take a lot longer to get through the system. And you can see most of these are from the early rounds. Unfortunately, as this project ends, we probably will never get a true picture of, say, the journal articles, because papers that'll probably come out for rounds 5 or 6 will come out after the project has ended and the final report's prepared. Next slide. Okay, one of the things we've been also following is the website usage. Part of our charge here at Penn State, we were to develop an online system for the coalition research portfolio management. Essentially, what we were looking at was online RFP release, proposal submission, and proposal review. I mean, all the PIs are aware of this. Any of those who are reviewers are also aware of this. Now, what I'm showing here is the usage from March 2016, when we pretty much got everything up and running, through June 30th, 2021. What ended up happening was, at that time, mid-2021, the university forced us to move our website from a college server to a university server. Of course, the analytics, the programs, I have data from 2021 on, and it looks a little bit different in its format. So I'm not showing that, because I'm also showing this because this was the period of most of the activity on UCFER because of the solicitation rounds. And for example, the big spikes in 2016, that was the round 1 and round 2 proposal submissions, reviews. Those 2 rounds had overlapped. And then round 3 was late 2017 to early 2018. There is a big peak there, big peaks yet in 2017, and I think that's because that's when a lot of people were taking a look at the program. That's when universities were looking at applying for memberships, so we expanded it. Round 4 was the first half of 2019. Round 5 was the last half of 2019, and then round 6 was in 2020. And so that's where you can see some of these major spikes. Next slide, please. This shows, it's called yearly website usage, but really this is for the college server. This will obviously, in the final report, will also contain information from the second server, because it's, our website's obviously up and running. And the files were highlighted because I'm not a computer person. I was told that was probably the category that made the most sense when you're looking at website usage. But what I did want to point out is, I had made the comment that we have coordinated other consortia in the past, and I was involved with the Carbon Consortia from 2003 to 2010, and so I looked at numbers there. And what I'm seeing here is the website usage in UCFER is probably about 10 times what it was in that program. And again, a lot of it can be attributed to the fact that we were using the website for the proposal submissions, solicitation, release, and reviews. Next slide, please. And these show some of the user demographics. And again, I don't really know what unresolved unknown is. You have to talk to somebody who's more computer savvy than me, but you can see that this breakdown, you have commercial, educational, US government, network, foreign countries, other consists of like nonprofits, the US military, generic business, and a couple of others. So you can sort of get a feel here of the demographics of the users. Obviously the homepage site's the most visited. When RFPs were open, members only page was very visited. And the other pages that are hit often are the newsletters, funding, project summary sheets, impact. And of these countries, there were 75 of them, and I've listed those that were some of the ones that were hitting the website the most. Next. Going into this a little further, and I wanted to show some information, and this is related to the round 3 solicitation. So in red there, you can see when the RFP was open, and then you can see the review period. And if you look at the files leading up to the RFP open and then after it closed, you can see, obviously you can see an increased usage. So you can see from this that whenever a solicitation was open and the review period was on, there was much activity on the website. Next slide. And then I just wanted to delve into this just a little bit more. Again, this is with the round 3. These you can see when the RFP opened, which was in November 2017, then it closed in January of 2018. Now you have to really pay attention to the y-axis. This kind of drives me crazy. We can't control it, but I don't know anybody, any engineer, scientist, mathematician that would have 7,529 as the upper limit. I mean, but if you take a look, you can see after a very strong initial peak, and each bar is a day in the month, and so you can see that it's still, still pretty it's high initially, then it levels off, and then at the very end, when everybody's submitting their proposals, it peaked again. If you look at the January one, you do see you see it increasing, and then there's 2 drops. Well, that's a Saturday and a Sunday. But you can see that there is definitely increased activity with the RFPs are open. Next slide. And you can also see it. You can also see more activity after during the review period. But if you take a look here, this is more similar, the hits over the entire period, and that's because this was a very active period for the Penn State, in that typically we had to invite 3 to 4 reviewers for each one that accepted the invitation, and it depending on how many proposals there were. I mean, these invitations, I mean, there were sometimes as many as 150 people invited, like in the one case when there were 80 proposals. So anyway, this just shows the usage during a review period. Next slide. Our outreach activities, well, we've been maintaining a website, which you see there, and then you saw from Omer's slide that the URL that actually takes you directly to the meeting presentations. We complete project summaries for all projects that have the final reports accepted. We have 29 of those right now posted. We are waiting on 2 final reports. We prepared the summer 2022 newsletter. The other thing we've been trying to do, and we need your help, and that is success stories. We started this last year, reaching out to PIs of completed a project. So far, we've had little response, but we're still trying. Next slide. This is an example of a project summary. This is from a round 1 project. This is the front and the back. This is what we prepare when the project's completed. We send it to the PI for review, comment, and then we post it. Next slide. I mentioned the success stories. This is the kind of information that we're looking for, that we're trying to find. New projects that have been funded as a result of the UCFER project, new commercial products, new patents or software. If a center has been established, even things like best paper awards, highly cited work, graduate student successes. So for those of you who are, still have ongoing projects, we're going to be hitting you up on this to see if you have anything to contribute before, before the whole program ends. Next slide. I mentioned we have started the final report. I mean, this, like I said, this is going to be massive. What you see in red here are the items that we have already completed. And these are, or at least first drafts are completed, and these are just the main, the main sections. Obviously, there's multiple subsections within them, and so because some of these activities, like the definitization period and the structure and all that was done early on, so that was something we could complete. Next slide, please. Again, you can see proposal submissions. What's still going on, obviously, are managing the coalition projects, summarizing the projects as they all end. Next slide, please. I'll be done soon. And then these are the last few sections of the final report. And next slide. And what I want to do in closing here is that so many people have been part of this program that to try to list them here is very difficult. But I do want to say in my closing comments at the end of the meeting, I have several slides that have more detail, and these will be posted on the website after the meeting. And if anyone notices that I've missed someone on that, please let us know and we'll add them. But it's obviously it's very difficult to try to list everybody, but we're trying, as the program's ending, to really call out all the people at NETL, at Penn State, at the various universities. And so we want to acknowledge, as you can see in the first bullet, NETL, I mean, just the various, I'll say, like categories. The member universities, those folks who served on the Technical Advisory Council and Core Competency Advisory Board. And then, of course, all the research participants at member universities and at NETL. I mean, that's the base of this whole program. And then early on, the Penn State leadership in supporting UCFER, and then those around me, those around me on our operations management team, and many others at Penn State. And with that, I'll conclude my presentation, and we're, I think, only a little bit behind.
Thank you very much, Bruce. There was a lot of valuable information there for NETL staff, so that was an excellent presentation, and I look forward to seeing what the update will be closer to when this cooperative agreement closes in June. So yeah, we are a bit behind on time, but that's okay. We can eat a little bit into our Q&A after this upcoming session. So Bruce, I will hand it over to you to introduce the slides as we proceed. And thank you very much again.
Okay, you're welcome. Excuse me. Yes, now we're going to have two presentations in integrated carbon management. And the first one is a project that's at the University of Pittsburgh. And there'll be two presenters here, Wei Xiong and Albert Tu. And so, Wei, do you want to take this?
Yes, thank you very much. Since my background is not very good looking, so I'll probably work close later. But then this is a very nice, exciting project. I worked together with Dr. Albert Tu from our university, and also collaborating with Chantal Sodbrock from NETL. And then we have been getting a lot of support from their side and having a regular discussion. And we're also exploring some experiments continue for this project. Right now, we're collaborating with different companies from Siemens Energy and Jeffertech, Haynes. So we have been involved in some of the discussions for the critical technical point. Next slide, thank you. So, we have some discussions on the outline first, and then this covers background, and we're talking about some of the report results, but then continue with some new observations and findings. Next. So basically, Haynes-282 is one of the several candidate alloys, which is very strong enough, up to 760 degrees C. Is Xiong available for the power plant, especially for the ultra high temperature range, ultra supercritical coal power plant. And of course, I think it will be also having a good potential for the future use with hydrogen energy. And then we want to reduce carbon emission. So next. We have been doing some of the WEM process before, but then I have to highlight GERVTech is one of the machines come from Germany development, and then we are the first one, and so far probably the only one in the United States having this big monster and producing all of these big parts. And then we do find a lot of challenges regarding the complex shape and the SIG work component. So this work is really dedicating to combine the experiment and supporting machine learning, data science to fuse it there together and to solve the problem with some of the location specific. So the first item is how to try to get the highest possibility with the strength and ductility, but also a very important thing is how to making sure that there is a kind of a uniform structure and distribution to ensure the distribution of the properties as well. Next. So this is a kind of overview with some of the background. I probably just want to highlight there are some complications regarding the carbides and strengthening particles formation. Next. And then, well, essentially want to reach the target of the property, which is similar as a raw material. However, again, very important thing for this project is to ensure that these big parts, you can have the uniform distribution of the structure and property distribution. Next. So we're going to talk about some of the things regarding the last view. Next. So far we have been working on this project for a while. Then we produce some of the different parts, and then we also investigating different patterns, the single bead and meander, which is zigzag. You practically will be involved in the production. Next. And then we previously were focused on how to making sure that we can reduce the grain size. For example, like we tested with the DTA measurement and determine the phase transition temperature. We identified 1250 degrees C will be able to get us like 2 hours with a minimum grain size distribution. Can solve the problem of the anisotropic with the grains. Next. So we also involved with big parts build, and then this is one of the examples we built with a cone-shaped example. It's really a large one. Next. We're going to next, discussing about the precipitation. So this is next. So this is the one that we are similar if you observe with a single bead and then meander melting pattern. So basically, you can observe some of the MC carbide highly concentrated with moly and titanium. And then next, we're going to talk about the strengthening particles. So basically, what are the differences? If you're talking about raw material, the choice of the homogenization or solutionization process using 1150 degrees C. However, in order to get reduced grain size, you have to go up to 1250 degrees C. And then all the consequence precipitation and gamma prime precipitation will be changed. Next. So recently we have been looking into the gamma prime precipitation. This is the most important one regarding this material. As you can see, 1150 degrees C with a homogenization, and then going with the MC carbide, you will be able to reach the peak strengthening around like 8 hours, 6 hours. But then if you use 1250, then you can actually push the time a little bit earlier, around like 4 hours or 6 hours. Next. So this also, kind of quick evaluation with the hardness. The good thing of the hardness is really you can actually starting with hardness distribution with a kind of mapping stuff, and then we're able to produce a lot of data versus doing the tensile one by one. So we want to have a good model and also understanding with the hardness involvement. So this is a kind of comparison where you have these two different choices with the processing and then contribution in value of the hardness. Next. So, but then we also need to making sure hardness representing the real testing results. But you know, we always learn things along the way once we do the research. And actually, it's not quite encouraging with some of the testing here. So actually, we find 1250 degrees C, we are actually not be able to reach the same property. It's actually significantly reduce the property compared with the raw material. So the reason why, go to the next slide, is actually very interesting. So I believe a lot of things were probably not going to look into this if you don't find a kind of difference like this huge. But then we indeed, there is a kind of trade-off as well. If you have reduced grain size, if you push the boundary a little bit higher with a crystallization temperature, then actually you will start to have more pronounced kind of porosity involved. So these two, the first one showed the as-built structure, you already have the ones. And then if you don't solve the problem, then it will be having more serious problem going on with the post-heat treatment. So instead, even though we try to avoid to use the hot isostatic pressing, but then we have to use this one. Then this is the one that after hot isostatic pressing heat. Next. So we are ongoing with evaluating the properties after heating, but then simultaneously we are also doing heavily with the high throughput experiment supporting our machine learning and simulation. Next. So we have, you know, designed kind of gradient temperature furnace where basically putting the sample into there, and you can get a kind of continuous distribution of the temperature, and then you insert the thermocouple into this. So this is actually utilizing the WAM process, the additive manufacturing, as a scientific tool to produce all the processing microstructure and property data in just one heat treatment. So we're focusing on doing the heat treatment, understanding of the precipitation strengthening at different temperature. So our student is still collecting the data and do the evaluation microstructure checking. Next. And then further go next. So with all of this data we're preparing, so we're going to use for the machine learning and high throughput computation. Next. So this is a model part that I'm discussing and working together with Dr. Albert too. So this is ICME contribution to understanding of the yield strengths. Basically, we have the yield strength model considering grain boundary strengthening, solid solution strengthening, and precipitation strengthening. And of course, most important parts will be related to the precipitation strengthening. Next. So we want to calibrate our model. Otherwise, then if you only have a machine learning with a model, then it's garbage in, garbage out. Right now we have experimental data. Then we calibrate the model and simulate and calibrate the model with the interfacial energy describing the gamma prime precipitation. Then on the left-hand side is showing the comparison. On the right-hand side is actually further predicting with the yield strengths with this model. And then we identify the sweet spot is around like 700 to 850 degrees C, and then you vary with a different time. And of course, you do have a potential to further reduce time with aging, but then this is a theoretical prediction. Next. So here we are actually showing you that this is a kind of model calibration. So we do have different agent heat treatment, but basically also we try to understand how can we fuse the data between the yield strength and the hardness, because again, hardness is easy to perform and then can supporting with the data mining and machine learning. So this is kind of telling us that the yield strength probably around like 2 times the measured hardness. Next. And we did some kind of preliminary study with high throughput experiments supporting the model calibration, but also supporting the data. And then we also step into the machine learning. So as you can see on the left-hand side of this figure, then we first use the experimental data to calibrate our model, because all of this model has the input of the parameter, for example, like the dislocation density and grain size and so on. So you have the physical model make a prediction as a red dot showing up here. But then certainly, they will have deviation. Therefore, we use a Bayesian calibration to further calibrate this model. Now you can see this triangle with the blue. And then this model is actually telling you a better fitting and prediction with the experiment data. And here, furthermore, you can do the machine learning and predicting all of these ear strings. And of course, right now it's just kind of, we are collecting all the high throughput information and then further refine this machine learning model. However, I have to draw attention again. So this is a kind of new stuff we also learn and be aware. So next. Of course, I can provide such a kind of, the plot on the right-hand side without saying that you believe, oh, this is a fantastic model. However, we have to also draw attention, understanding the physics. So basically, this is kind of a little bit overfitting we find. One of the reasons because we haven't yet get really a good data sets to train. That's the reason why we place the high throughput experiments serve a very important unit in this world. And then if you look at that, the feature value means, the gamma prime is very important. However, if the model predicts if you have more gamma prime, then it's actually going to be worse with the strengths. Certainly this kind of, non-physics involved with some of the model prediction. So far, we're hoping that, high throughput will be able to help us to get more data to correct this model and then get a more reliable physical prediction with the machine learning method. So next will be Dr. Alberto's part. Next. Yeah.
Everyone, can everyone hear me?
Yes.
Wait, can you hear me? Okay. All right. So we in this project we're contributing residual stress modeling in the YR process. So the approach that we're taking is both like physics-based simulation as well as using machine learning to accelerate the prediction speed. So for this work, what we're trying to use is actually instead of using machine learning only, we try to use transfer learning to accelerate that learning process. Next slide, please. So let me explain a little bit what we are after here. So previously, we've been working on modeling the residual stress and distortion on the laser power back fusion process. So in this case here, we do physics-based simulation to generate the data on 800 different geometries to create a database. And then we use this machine learning model called a bidirectional convolutional long short-term memory neural network, a long name, I know, but so we use this neural network to do the machine learning for these like 800 geometries that we perform physics-based simulation on to generate the data basically, and then put it into this neural network to train the model in order to predict residual stress. And then of course like we have to test and do testing and validate the neural network on its prediction. So what we did here was we take an unseen geometry. So the geometry on the right hand side, which is a cantilever beam structure with T support, and run it using the neural network, and then we find that the result is quite close. So using the data-driven approach based on the machine learning compared to physics-based finite element simulation, the average error is about 7.7%, which is not bad. Considering that this geometry is unseen, it's not actually in the library, it's not in the database. But the key here is that we want to improve the efficiency. So, if we were to do the residual stress prediction using ANSYS, you would take like 930 seconds. And then using our in-house code, which is based on GPU computing, it takes about 255 seconds. But using this machine learning approach, the prediction becomes like very, very fast, only takes like 0.1 seconds. So the bottleneck here, I'll show you some example on the physics-based simulation or the YR process. But typically for a part, even reasonable size, it may take like several days, even using a GPU-based simulator, which I think is very fast already. So in order to speed that up, we want to use like machine learning. So the way that, next slide, please. So since we already trained this neural network for laser power bed fusion, so our thinking is that can we take advantage of this neural network that has already been trained for laser power bed fusion and do just a little bit more training and convert that into something that we can use to predict residual stress for the YR process. Okay, so here's the architecture. Right? We have basically, different layers in the neural network, and there's some layers that are very specific on geometries. The interaction between the different geometric features within a geometry and among different geometries. But there's another layer called the CNN, the convolutional neural network. They're more process and material specific that, we can actually replace that. Next slide, please. So we can replace that, we train the convolutional neural network. So these are the top few layers in the entire neural network that will be retraining using YR physics-based simulation data. So instead of doing the entire 800 geometries again, we're going to do, selected geometries using YR process parameters and material properties. So next slide, please. So we have done already developed a process simulation for simulating Higgs 282, using the YR process, and already developed a model to simulate, something like cylinders. Even for this very simple geometry, 22 layers, it takes the GPU-based simulator about 1 day to simulate this geometry. Next slide. And then we already have done experimental validation on our model. Basically we attach thermocouples, on the build plate, on the geometry, 5 thermocouples, and then calibrate the absorptivity, convection boundary conditions, so that we can match with these measurements on the thermocouples. Next slide, please. So we are in the pause. So we need data still for the transfer learning training. So we try to use 20 geometries instead of 800. And then so right now we're working on getting the results from the final element analysis. And so we have trained about 15. We have generate data for 15 different geometries, so a few left, and then we'll start the process of training after that. Next slide, please. Yeah, so finally we'll validate, the prediction by the machine learning model. And so we already have some experiments doing that, and also, we can actually use a physics-based simulation to generate data, also to compare with prediction from the machine learning model. So yes, so I think that's all I have for this presentation. Thanks.
Thank you. We only have 2 slides left. Can you please go next with the future work next? So we're trying to wrap up with this short project. We learned quite a lot. We also, kind of balance how to, fuse all the work together. So we're planning, continue with this high throughput experiments and further finish up and getting a good kind of prediction with the machine learning. And we also want to really push as much as we could regarding the strength and the elongation. And so far, we're testing some of other things after the heaping process. And then we also want to making sure that we have the uniform distribution of the structural properties. That's the most important one. And certainly for Albert, he will continue with his machine learning and try to understand what are the things we can control with the cylinder shape sample. Next. So, after that, we also talking with Chantal at NETL. We planning to do some strength evaluation, high temperature, if possible, probably creep longer time, but then if not possible, at least high temperature can do that. And then we're going to crack on the cone-shaped sample and see if the distribution is well with a uniform distribution. Next. So basically, this is a dissemination. We have one already popular work in General Materials Processing Technology. We already submitted 3 papers and 2 went to the 718 conference. We have multiple invited talk and 2 invited talk in the coming conference and 1 student talk. That's all. Thank you. Thank you very much.
Thank you. Thank you, Wei and Albert. We'll go right into our next presentation. The second presentation is going to be given by Michael Mueller from Princeton University, and this is also in the integrated carbon management area.
All right, fantastic. Well, hopefully everyone can hear me, and it's a pleasure to be here to talk about our project this year. I have to acknowledge a postdoc working with us, Pepe D'Alessio, who stepped in last year when I had a personal conflict. So at the end, just if he did a much better job than me last year, just don't tell me that. It won't help, you know, the relationship here with a fantastic postdoc. So thanks to our previous speakers who kind of alluded to the area of machine learning and database modeling, which is the topic of this project, which is a collaboration between myself and Sankaran Sundaresan in chemical and biological engineering here at Princeton. And so if we go to the next slide. I mean, the basic motivation of this project is from the computational science standpoint. The era of big computing has opened up an opportunity to leverage huge amounts of data that we have available to us and to leverage this in a smart way. And so the underlying question that we're seeking to address in this project is how do we leverage this increasingly large data from high fidelity simulations to help us develop closure models for coarse-grained flow simulations. And the next slide, please. And the specific application space that we're thinking about here is multi-phase reacting flows. So things like fluidized bed reactors that are relevant to a wide variety of not only current, but future energy conversion, storage, and chemical processing devices. And so the basic idea is, you know, on the left, you have a very high resolution, high fidelity simulation that's extremely expensive to run. And so the question is, how do you leverage this data in an effective way to develop the closure models you need for coarse grain simulations, say, that you have on the right? And traditionally, the way this is done is we look at the data, think about it for a long time, and come up with a good idea for a physics-based model. But this is not always extremely fast. And as Director Anderson mentioned this morning, there's certainly a time factor in the decarbonization process. And so the question is, how can we leverage machine learning and database modeling to do this much faster, much more systematically? So next slide, please. So there's 2 parts of any database modeling framework. The first part is the training part, which is an a priori part where you take the input or training data that you have available to you from a high fidelity simulation, you process it in some way, you filter it, coarsen it in some way, you train your favorite flavor of neural network or other type of machine learning algorithm to predict some quantity of interest that you care about in your coarse grain simulation. And the challenge here is that this training process typically requires a lot of very user-specific expertise to tune the various architectures and hyperparameters that go into your neural networks. You typically have to process the input data. And so this is a very labor-intensive manual process that's not particularly fast. And so what we sought to develop through our UCFER program was a more automatic and efficient framework to do this, where one could, you know, without sounding cliche, push enter with a data set and get a neural network model for what you care about. Then going on to the next slide. At the same time, then once you train and build these database models, you also want to then use them in a coarse grain simulation where you're taking as an input information from your coarse grain simulation to predict something that you care about that's unclosed. And so if you make some extremely bloated database model that's extremely expensive to evaluate, even though it might be a relatively accurate model, it might be extremely expensive to actually evaluate an a posteriori simulation. And so not only do we want database models that are automatic to train, that are efficient to train, but they also need to be relatively simple such that we can quickly evaluate them in our coarse grain simulations to take advantage potentially of the accuracy that we can achieve. So the next slide, please. So this is the basic kind of workflow that we've developed as part of this project. And I won't go into all the details on each of these parts, but we take essentially the raw input data from our high fidelity simulation. We get rid of statistical outliers. Perhaps there's some downsampling that we need to do in a pre-processing step. Then we start to build our model. And the first step in building a database model is to decide what to use as inputs. And you want to use as few inputs as possible to make it easy to evaluate, but just so you don't have to carry around as much information when you do the a posteriori prediction. I'll talk a little bit about some of the work we've done with an approach I'm calling dimensional consistency in the last few months. And then finally, once you've figured out your inputs, then you have to actually train your model, which is basically an exercise in regression and optimizing the hyperparameters and architecture of your neural network. And finally, you get your output. And throughout all of these stages, the philosophy that we've had is we want to make this as automated as possible and as efficient as possible and as simple as possible. So the next slide, please. I won't talk any about the data pre-processing this year. Pepe talked about some of that this year, but of course, if anybody has follow-up questions, feel free to reach out to ask questions about that. So next slide. So I'll talk about a little bit of the work we've done in dimensionality reduction using this concept of dimensional consistency. So the next slide, please. So just as a starting point, this is the typical way that one would approach database modeling is you have some data set. Here we did a test in a reacting flow. So this is a set of just jet flames, and we want to model some quantity that we call the progress variable dissipation rate. That's essentially a mixing rate, and this is important for modeling in various homogeneous chemistry models because we often make a mixing chemistry balance type of assumption in these models. And so this dissipation rate model is a key input quantity that we need. And so we need essentially the coarse grain analog of that, which is the filtered dissipation rate. And we choose a variety of inputs that this mixing rate could depend on: the progress variable itself, so a composition variable, its gradient, a flow characteristic, a strain rate, a filter size, molecular transport property, the diffusivity, a chemical source term, and the density. You know, not unreasonable things that this could depend on. Then using these inputs, we train then a model for the dissipation rate using a deep neural network. And so if we go to the next slide, what we get is something that looks pretty good. The black points are the high fidelity simulation results. The red points are the red line is our database model, and the dash dotted blue line is some traditional physics-based model. And so the accuracy is quite good compared to a traditional physics-based model. The challenge becomes, if you look at this architecture size, it's an enormous neural network that is extremely expensive to evaluate in a forward simulation. And so if we move on to the next slide, one thing that always bothered us is that the progress variable dissipation rate has dimensions of composition squared per time, and all of these inputs that we started with all have different physical dimensions. And so what you always do in a database model is you rescale everything to make it all dimensionless, but the starting point essentially starts from things that have different physical dimensions. So the idea we had is, well, let's take our dimensional inputs and form groups that are consistent in terms of their physical dimensions with our output quantity, so composition squared per time. And so if we do that, we take our 8-dimensional inputs, and that then is reduced to 5-dimensionally consistent inputs. And as it turns out, the set of groups you have is not unique, but it doesn't actually turn out that it matters how you group these things together. So we said, okay, well, let's then take these dimensionally consistent inputs. That's a smaller input space, although we haven't really lost any information. We know physically everything needs to be dimensionally consistent, and see what happens when we then go ahead and train our deep neural network. So if we move to the next slide, what we found was quite remarkable. This is on the right now is our dimensionally consistent inputs. The accuracy is actually a little bit better in a quantitative sense by about a factor of 3, although in this kind of conditional mean plot here, it looks about the same. But our network architecture, the network got much smaller, so faster to evaluate in a forward pass, and the training time went down. And so we reduce the dimensionality of our input space simply by using physical dimension arguments, and we got something that's a smaller network, that's more accurate, that's faster to train. And so that's really things that usually have to play against each other, not things you all get at once. And so it's a no-brainer there to do this. So if we go to the next slide, alternative ways to reduce the dimensionality of our inputs, of our original input space, would be to use something called principal component analysis, which is a purely data-based way to do this. And so if we compare our approach using physical dimension arguments compared to 2 different ways to do PCA, and I won't make a distinction, what we find is kind of this physics-based way to do database modeling in some sense. It gets you a network that's always smaller, more accurate, and faster or as fast to train as these approaches using dimensionality reduction using data-based approaches. And so this was quite exciting to us, and it kind of proves a point that, you know, just throwing away all the physics that we know about isn't necessarily the correct way to build data-based models, but with this idea of physical dimensional consistency, you can still automate this in a relatively straightforward way. And so one of the open questions that we want to explore in the remainder of our project time is, once we form these dimensionally consistent groups, does that actually give us an opportunity to do additional dimensionality reduction using these data-based approaches such as PCA? So we'll have an answer to that hopefully for the final report. Next slide, please. I'll skip this one in the interest of time, and I'll go to the next slide. Okay, so that was a bit on some of the recent work we've done on dimensionality reduction. Let me say a little bit about some of the recent work we've done on the modeling side. So next slide. So one of the challenging parts of database modeling is the first question you have to ask yourself is, what regression approach should one use? Opposite extremes, linear regression is the simplest, machine learning algorithm in some sense. You can do this very quickly. It's not very accurate if you have a nonlinear problem. On the other hand, neural networks are very accurate, but it takes forever to do the training and potentially the evaluation process. And so the idea that we came up to be more efficient is essentially to use both. We take our data and we cluster it, and in some clusters we can get away with a locally linear approximation, and in others we'll have to use a neural network to account for nonlinearities. This seems to go a bit against our automatic and simple idea, because now we have added this additional step of clustering, but we actually developed a strategy to automate how one would do the clustering based on a minimization of something called the Davies Boolean index to get the optimal clustering. So we showed that this approach is quite effective. We did some application on a reacting flow problem and showed that you can actually get the accuracy of one giant neural network with this kind of hybrid approach, but with 10 times less training time to get the database model, which is certainly an accomplishment. So next slide, please. So then you have to train a neural network ultimately, and the challenge always is the common way that this is done is with a lot of hand tuning with people who have expertise in building these neural networks until they find an error that you find acceptable. And certainly hand tuning is not an automatic process. And one of the things that often comes about to minimize the amount of hand tuning that one has to do is you typically get very, very large suboptimal neural networks that in most cases overfit the training data that you have. And so that again is contrary to our kind of basic philosophy of this project. So if we go to the next slide, the first idea that we had that kind of is in the project title itself is to kind of borrow ideas from other areas of numerical analysis and to kind of iteratively find the best set of hyperparameters, so the number of layers and neurons per layer in a neural network. In the following way, you would train your model, you figure out then its error. If your error is good, you're done, of course. If it's not, what we do is we assume that the error behaves as a power law fit with respect to the number of neurons and layers that you have. And from this power law fit, which basically follows the ideas of like grid convergence and those types of ideas of numerical analysis, you then do an extrapolation to get the neural network size that you expect to meet your error threshold. So this actually works quite well. It's very automatic. We found that compared to kind of other automatic ways to do this type of optimization using either random searches or grid searches, it can be twice as fast as those in terms of training, but it does tend to lead to relatively large neural networks, and that's just because the power law fit is not mathematically rigorous by any means. Works, maybe not the most effective. So if we go to the next slide, what we've been exploring in the last year or so is a different approach using Bayesian optimization, which was pioneered by one of my colleagues here in computer science, Ryan Adams. And so the idea is that you essentially build a probabilistic model whose design space is the various hyperparameters and architecture inputs of your neural network. And then you pick some acquisition function that you're trying to basically minimize to figure out where you should look next in your design space. So you can almost think of this as a smart random search or a guided random search. And one advantage of this compared to our first approach is that you can put everything else in your neural network architecture in there as well. And there's a variety of acquisition functions that one can choose, but to make a long story short, I'll show some numbers in a moment. This acquisition function based on the lower confidence band, which is essentially a greedy algorithm we found, tends to be the best across a variety of application problems. So if we go to the next slide, what I want to spend is the last couple of minutes showing you some applications and then including some of the collaborative work that we've done with NETL. So next slide, please. So as the application that we've kind of done in-house, we took some training data from some two-fluid model, high-resolution two-fluid model simulations from Sundar's group. You coarse in that, and then you get a very coarse-grained simulation. The inputs that go into this model are the Reynolds number, the filter size, the solid volume fraction, that's what the colors are on the right, the normalized pressure gradient, and a slip velocity between the particles and the fluid. And what we're trying to model is essentially the filtered particle drag, so the drag between the particles and the flow at the unresolved scales. Here we're just using a giant neural network using our Bayesian optimization framework. And one thing I didn't put on the slides I should mention is we've actually made this particular model that we've developed here publicly available and have interacted with some industrial collaborators who have used it in their in-house tools as well. So next slide, please. So this particular training data set had about 10 million points, and so it's a good test because this is a relatively significant data set that you wouldn't want to sit around doing things manually. And then in this table, I just show how these different Bayesian optimization acquisition functions behave. All of them give the same error in the end, but this lower confidence bound approach we found have always led us to the smallest neural network, which is going to be the quickest to evaluate and with a much shorter training time, which is an advantageous thing. And so one of the open questions that we want to answer in the remainder of our project is we have these two approaches to kind of finding the best neural network topologies, the one based on this convergence rate idea, and then this Bayesian optimization approach. And we want to look at the pros and the cons of those two approaches relative to one another. So next slide, please. And so, you know, one of the criticisms in the physics modeling community about these data-based approaches is that everyone treats them as a black box because you can. And so one of the things that our postdoc Pepe's been doing is trying to understand if there's any insights that we can glean from opening up the black box. And so for the filter drag, one of the things that he found that was quite interesting is why this vertical coordinate y is not exactly the filter drag. It's a slightly different quantity, but the point is the same. It ends up being a linear function of the non-dimensionalized pressure gradient. And so what he was able to do is actually recast how he does the training and explicitly use a linear relationship with respect to this non-dimensionalized pressure gradient, and found that this actually helps then when you use this in a posteriori sense, because you essentially have a constraint on how it behaves with respect to the pressure gradient in a linear way, rather than kind of an unpredictable extrapolation one might have, leaving everything to a neural network in the end. So next slide, please. So let me then spend the last couple of minutes I have talking about the work we've done with NETL. So in parallel, but not necessarily coordinated with us, the MFIX team at NETL had been working on coupling data-based models for the filter drag to coarse grain simulations in MFIX. And one of the challenges that they had is they weren't able to really get good results with neural networks because they had trouble finding the best set of hyperparameters and architecture for their neural network. And so this was a really good opportunity then for us to leverage the framework that we've been developing to kind of work with them to improve the capabilities that they have there that can be implemented into MFIX. And so if we go to the next slide, what we did is we took then the same data set that the NETL team had been working with in their work, and we applied our framework to that. Just to get things rolling earlier this year, we started with a smaller data set that only had about 6,000 samples. Rather than use a neural network, we used a different approach called Gaussian process regression or kriging, but the process underlying it is more or less the same from our perspective. And we trained a model then for the filter drag, and the starting point that we took from NETL had a particular error and regression coefficient. And then as we used kind of the vanilla version, reduced the input space using PCA, and then cleaned up the data, we could get a precipitous decrease in the model error and a better regression coefficient on this small data set. So proof of concept that we can indeed increase the fidelity of the MFIX tools. And so what we're working on next is we'll take the full data set, we'll switch to neural networks and our adaptive regression approach to see how well we can do compared to the existing capabilities that are there. So next slide, please. So that's the basic idea of our project is really one focusing more on the process of developing data-based model. The application space is kind of these fluidized bed reactors, but this basic idea, of course, extends to a number of other applications. In the next slide, the final slide, let me acknowledge great work. So Dr. Pepe D'Alessio is a postdoc working with me, and Sundar has done a great job. And we also have Mr. Christian Lacey, a graduate student working with us on this as well. He did a lot of the dimensional consistency work. And then another postdoc, Mustafa Suleiman, did some initial work at the beginning of the project on some of the a posteriori work. Christian also spent a couple of months at Sandia as part of an SCGSR fellowship funded by BES to kind of take the ideas and apply them in a slightly different space. And then I also need to acknowledge some of the internal funding from Princeton, some fellowship support of Christian, as well as the research computing resources they provided. So that is it for me, and I think I will just leave it there.
Great, thank you very much, Michael. So our Q&A session in the agenda had a dual purpose. It also serves as a good buffer in case any of our previous presentations went over time, which is the case now. So we won't have time to go into Q&A, which is fine because I don't quite see any questions in the chat box or in the Q&A box. If you do have any, please submit them so that either of our presenters could answer them offline or later. So we do ask those who presented, and thank you, by the way, we do ask those who presented to stay on, and just in case some questions come in that you can answer via either the chat box or the Q&A box. So we're going to head into lunch and we'll reconvene at 1:05. What I'm going to do is maybe 3 to 5 minutes before the end of our break, I'm going to ask these speakers who are on the screen right now to hop on and do a quick mic check. And so that way we just make sure all your equipment's working. So without further ado, let's break for lunch and reconvene at 1:05. Thank you. So, excuse me. So, yeah, Bradley, you have the floor.
Awesome. Thank you very much. So, my name's Bradley. I'm with the University of Kentucky, and I'm going to be talking about the development of our novel process intensification device called acoustic-driven packing material. Next slide. So before I get into it, I know there's some people here that may not be familiar with what packing material is, but essentially it's just a type of corrugated material that provides extra surface area for reactions to take place. They're used in a wide variety of different chemical processes, from CO2 capture, obviously, to distillation and general separations. Down here on the left-hand side, you can see this is a 3D rendering of the column that we have been conducting testing with. And on the right-hand side, I just have a little picture of what the packing material would look like in a full-scale commercial size setup. So the primary research for this is for CO2 capture, but because it has such a wide market applicability, it makes it really good for trying to create an SBIR or push this technology further, because the market landscape for CO2 capture at the moment is still growing. Next slide. So I want to talk about the mechanism of acoustic-driven packing material, how it works, why it works. So you can imagine that we have some sort of acoustic source, whether it be, it'll likely be a transducer of some sort. This will be affixed to the packing material via some means, either directly or later in the presentation, I'll discuss air coupling. As the transducer transmits the acoustic waves into the packing material then becomes a resonator of that power at similar wave parameters to the transducer. The liquid film that's coating the surface of the packing material will then begin to oscillate up and down, and this oscillation provides excess surface area beyond which the packing material was able to provide just by itself, as well as create lots of turbulent flow and promote micro level mixing. Next slide. Our overall goal is to reduce the size of our absorber column. So looking at our cost estimates for a 60-foot absorber, it's going to be around 84.6 million. And if I can achieve a 30% enhancement in mass transfer, then I can reduce costs by up to 26%, dropping that price down to 26.1 mil. And this is going to work because with the acoustic transducers providing extra surface area, you're not going to need as tall of packed beds. So you can get that height reduction. Next slide. The path forward. So this is where we're at, and this is where we've come from. Started out with the proof of concept, just using a simple absorption setup with a sonication bath. We saw positive results. We moved that up to a proof of application setup in our 2-inch column. It's just a multiple pass-through absorber only. We saw the same results that we saw in the proof of concept. And we attempted to create our first working prototype. It was successful, but we did run into a lot of difficulties, especially with maintaining resonance. And then we started talking with a company in Switzerland called MPI. They have a fantastic method for maintaining resonance in a column. And this brings us to our 3-inch bench scale testing. And that is what I'm going to be talking about for the rest of this presentation. Next slide. So the research goals that were set forward, we have solved the resonance issue with the use of the impedance matching technology. So what ends up happening as you're in operation, the solvent travels down the column. This changes the natural frequency, and this can cause your transducer to fall out of resonance and shut the whole thing off. But with this impedance matching technology, we're able to maintain resonance and have continuous operation. So we've solved that. We've designed and constructed our column. We've done our performance testing with our 30 liter per minute CO2 captured bench unit. We've completed testing with MEA, monoethanolamine. We've quantified our performance enhancement, and we've investigated our power consumption. All that's left to do now is we have to add our solids to see how that's going to improve our capture, and then we're just going to test the second solvent. Next slide. This is our 30 liter per minute CO2 bench capture unit. It is equipped with the latest controls management system. It has a pressurized stripping unit attached. We're using CO2 in-house nitrogen for the supply. Yeah, and there's the location of where the column is currently at right now. Next slide. So last time I left you all off, this was our hybrid design. We had worked with MPI over multiple trials, and we've come up with this design. Effectively, it is packing material welded and then connected to 2 tube ends, and then the acoustic transducer will then provide power that'll transmit throughout the entire column. Next slide. Yes, if this was not a PDF, these are actually GIFs, and it would show you how that acoustic power moves through the column, and we get a displacement in the packing material measured on the millimeter scale. Next slide. But unfortunately, that design had one fatal flaw. We couldn't weld the packing in any sort of acceptable manner. It was just too thin, it was too flimsy. So we had to redesign yet again, and this was the motivation behind our final and current design that we have been and are still testing with. So if we just apply the acoustic power to the outside of the column, then the power will then travel into the column via air coupling, and it will then make the packing material inside resonate. Next slide. This is basically what it looks like. As you can see, it is a solid stainless steel tube with a transducer fixed to one end, and the packing material is resting on these Teflon shelves. On both ends, we have a decoupling flange. I'll explain that here in a bit. Next slide. So here you can see our Teflon shelves. These were milled from solid sheets of Teflon. I think I've made 24 of them in total. They keep the packing material from touching the column wall so that the air coupling is effective, and they also serve by pulling the solvent off the walls and redistributing it back into the packing material. Next slide. So this is really cool. This is our spring flange. In a lot of meetings, people wonder, how are you going to keep that acoustic power isolated to the column? Wouldn't it travel to the pumps, to the stripper? These flanges here, they act as a decoupling spring. As you can see, there are channels milled into them, and it effectively isolates all of the power to the column itself. And I had to install a little packing shelf, but other than that, next slide. This was our first set of testing done. These are the best conditions for our first round of testing. We tried at different flow rates, and I think it was between 300 mils a minute and 500 mils. We tried at different stripping temperatures, and the best condition was condition 2. We saw an 11% relative bump in capture, and our power was set to 800 watts, but the actual consumption was around 600 to 620 due to the regenerative nature of operating at resonance. And at condition 2, we can see a slight bump in our rich loading, which is an indication that we are indeed capturing more CO2 with the acoustics over the baseline. However, next slide. When analyzing the temperature bulge of the baseline and the acoustics, we noticed that the temperature is really high. At first, we thought maybe, well, this is just an increase in reaction rate, generating more heat, but actually the way that this system is set up, a few hundred watts of the acoustic power are being converted directly into heat, and they're heating up the column. So, next slide. So we're going to cool it. The reason why you want to cool it is now we have two things that are possibly improving capture. One is the acoustics, and the other is temperature. So I want to decouple the two, so I can just look at the improvement just from the acoustics itself. So we built a little shower curtain, pretty straightforward, sprayed some house water on it to cool down the column. And next slide. These are our results. We were able to reduce that higher temperature bulge back to the baseline levels, effectively removing any questions on whether or not the increase in temperature is actually what we're seeing, improving the capture. Next slide. So this is the MEA testing of these over with cooling, and to no surprise, we did see a slight reduction over that 11%. Condition 2 was about 5%. Condition 4 at the higher flow rate was between 6 and 7%. So this got us thinking, why are we not seeing a higher improvement? All of our other testing, we saw 30%, and we're only seeing 5 to 8% depending on conditions. What we basically came to the understanding is that our absorber column is just too efficient in the baseline state, and our stripping unit is already operating at its maximum capacity. So we decided to remove 50% of the packing material and rerun the tests. Next slide. These are the results. By removing half the packing material, we reduced our pack bed from 6 feet to 3 feet. And rerunning condition 2, we saw a, Is everything all right?
Apologies, give it a second. May have closed out accidentally.
All right, so by removing half the packing material, we effectively cut the residence time of the flue gas in half. And from this, we were able to realize a 19.63% relative increase in capture. This is more in line with what we have seen in our prior testing. And this is a great success so far. Next slide. So with the 6-foot column, we saw just due to the trend or the well, yeah, I can't say that word. Sorry, just due to the acoustics. I don't know why I had such a hard time with that word. We saw a 1.229 mole per hour capture just with that alone. By dropping the packing height to 3 feet, that increased to 3.326 moles per hour. That's a 2.7x increase. So why? Why is because we reduced the resonance time, and therefore the acoustics had more of an opportunity to be more effective because the column is itself less effective, and because of micro and macro scale mixing matters. Additionally, if we don't take into account the cost of power for the acoustics, we realize an 18.7% reduction in regeneration power consumption. Ideally, we are quite limited in this 3-inch bench scale testing rig because we want to achieve about 5 to 6 feet per second flue gas, but our operating capacity is only 1.45. So these results show a very interesting niche. Let's say there's some sort of steel mill and they are producing CO2 and they have a CO2 capture and they're cleaning up their CO2, but then they want to expand and they build another facility on site. Instead of building yet another CO2 capture facility for that or spending more money to upgrade their current one, they can just equip it with ADPM and they'll be able to remove even more because you're able to use it to increase the capacity of already existing systems. Next slide. So how does this look like in terms of column height reduction? So we took our results from our 3-foot and used Aspen to model it at different packed bed heights. That's the orange line. And then we looked at our results from our baseline experiment at the 3-foot and 6-foot level. And by using these models, we were able to extrapolate where the 3-foot model would meet the 6-foot baseline. And that was about a 28% reduction in column height with ADPM. This means that we have achieved our goal as advertised in our solicitation, our proposal, sorry. Next slide. In terms of power consumption goes, it's particularly difficult to estimate how the power is going to scale up with larger and larger scales. It has a lot to do with geometry and how it would take millions of dollars and time to do this. However, I did plot the power consumption as a function of technology evolution. So starting from the proof of concept all the way up to our 3-inch bench results, we are seeing a logarithmic decline in power consumption, that is kilojoules per mole CO2 captured. And interestingly, the way our 4-inch bench is set up, and with the current setup we now have on our 3-inch, we can take that and apply it directly to our larger scale 4-inch bench, and I was able to make a prediction for that as well. So it's really a cost of scale. The higher the scale, the lower the cost. And of course, this will plateau at some point, but I don't foresee it plateauing anytime in the near future. Next slide. So speaking of scaling up, we obviously cannot resonate an entire 60-foot column the way that we're doing now with our 3-inch column. So this got us thinking about using air coupling, since we are already using air coupling as the primary mechanism by which we are transferring our power to the packing material. So this got us thinking that we can just design a simple resonating tube attached to one of those spring flanges, and then we could just strap this onto the side of a column at a opportune position, and it'll effectively provide the same results. And it would be much more cost effective, it would be modular, and much easier to deploy. Last slide. I think my time is about up, and I just wanted to thank everybody at DOE, NETL, Dustin Brown, Benjamin. Thank you for all your help and ideas, criticisms. I really do appreciate it. And at CAR, I want to thank Kunlei, Roger, and Lisa. You've been great. And that's it.
Thank you, Bradley. With that, we'll go into the second of the 4 presentations in point source carbon capture. The next presentation will be by Xiaodong Hu and Junior Nasah. It's going to be they're going to do it together. Go ahead, Xiaodong.
Thank you, Bruce. Good afternoon, everyone. Yeah, our project is to develop a solid adsorbent from lignite-derived humic acid for CO2 capture. I will present the first part of the project, which is about the adsorbent development and characterization. My colleague and Junior will present the system design and testing side. So our project manager is Dr. Carl Laird, and our NETL collaborator is Dr. James Hoffman. Yeah, and before my presentation, I want to give a special thank to James, who is really an expert in this field with tons of experience, and he attended our monthly meeting and asked a lot of good questions and gave us so many good suggestions. So this project even has been started pretty late, but we can still catch up pretty well. So thanks for that. So next one, please. So this is just a quick outline, and we'll talk about the goal and objective and the proposed technology and scope of work. And most of the presentation were about the current progress, and then end up with a summary. Next one, please. So this FOA is seeking transformational technology for the CO2 and process combustion CO2 capture. So we are targeting to develop a low cost and multifunctional sorbent for that, and the capacity goal is greater than 2 millimole of CO2 per gram of adsorbent, and then with this half-time absorption, less than 30 minutes, and then need a good selectivity, or so balance with good cycling performance, and last but not least is the cost. So next one, please. So this torque technology is a kind of pretty straightforward process. It's a three-step process. So in the first step, we extract the humic acid from the lignite. Humic acid is the main organic matter of the coal. So we use potassium carbonate as solution to extract this humic acid. And then in the second step, we make this spherical adsorbent. And then in the third step, we kind of do a chemical activation to get the final adsorbent. So in the original proposal, we are trying to add a second ingredient, the PEI, for the CO2 capture, and then later on we find this one it works well even without a PEI, so which I think is important because PEI is much more expensive than the potassium carbonate. So next one, please. So we divide our scope of work into 6 tasks, and the task 1 has been finished since last year. So we get a procedure developed for the extraction of humic acid for the coal, and then task 2 and 3 will be the solvent development and characterization. So task 4 and 5 and junior will cover that for the CO2 system design and testing. So task 6 is the TA analysis. Next, please. So currently this is where we are. So we have finished all the 4 tasks, and we are on the last 2 tasks. Basically, we are testing a bench unit on the task 5, and we just started the task 6 of the economic analysis. Next one, please. So this is the current progress on the adsorbent synthesis and characterization. So this SE image you can see we have obtained those particle size around 1 to 5 micrometer with a pretty uniform size distribution. Most of them are pretty spheric. And then we also measured the surface area by a PET analyzer, and also compare that with the calculated surface area, and we assume the geometry is a perfect sphere, and those numbers are matched very well. So we also tested the CO2 capture capacity by a TGA. A typical result is like a few percent. This one gives a 9.6, which is greater than our goal. And next, please. So to study the synthetic condition, especially the particle size distribution and the chemical composition on the CO2 uptake, so we designed a series of experiments to optimize those synthetic conditions. So one parameter we try to develop here is called a particle size distribution index, and that is defined by the mean volume particle size over the mean count particle size. So with that, you can see in the graph on the left, if this number is close to 1, that means it's a perfect sphere. So we have a couple of them are pretty narrow, like 1, 2, 3, 10, 9. And then we measure the CO2 capture capacity, and then the takeaway here is we find the particle size and the size distribution in our testing range has a less, impact than the competition, which is not a surprise because you can see from all the 16 tests, those particle size or size distribution are pretty consistent, very close to each other. So next. So then we did a deeper understanding on how the synthesis process and the activation step impact the composition. So the two SEM image on the right shows you it's a cross-section image, and we did a SEM EDS analysis. So and then put those chemical composition in the middle graph. So the before and after activation, which you can see the orange is the potassium carbonate, the blue is the humic acid. So you can see in the inner shell, and humic acid is kind of less, and potassium carbonate is a dominant component. In the outer shell and the center shell, you will see humic acid is a little bit higher, especially after the activation. You will see humic acid is significantly lower. So that means in the activation step, the humic acid decomposed, so that exposes the potassium carbonate. So with that, I will hand it over to my colleague, Junior. Yeah, Junior, it's your turn.
Yep. Just to confirm, can you get me? I kind of missed the mic check since I was in the panelist.
Yep.
All right. Okay, good. Next slide, please. Okay, so what like Xiaodong mentioned, I'll be talking about the static testing that we've done and the bench scale testing. So with the materials we've made so far that Dr. Hu presented, so they are very fine. They're single digit microns. So one thing we decided to do for a static test, what we originally planned was we'll evaluate these in a TGA, thermogravimetric analyzer. So we would flow a stream of CO2 over the sample and then see our uptake as a function of temperature, and then also do some desorption to see how much CO2 was picked up. The first thing we kind of noticed when we did this, and we did a blank run, and in the blank run there was no CO2 in the sample. The first thing we noticed was, our sample loses weight. So in the process of doing that, a sample has there is a weight loss observed, and that was primarily moisture in the sample being lost. So we kind of find out that the sample was very hydrophobic. And that raises a challenge, because with potassium carbonate, your primary capture mechanism is the formation of the bicarbonate. So moisture is important in your analysis. What was interesting though, as we analyzed both samples, was that for the activated samples, we do see a overall gain in weight of the sample, meaning that we are definitely picking up CO2 over the baseline. That's the graph to the left of the screen. Meanwhile, when we try to run an unactivated sample, we see significant weight loss in both cases. So somehow the activation step does help improve the capture performance, which is kind of in agreement with the SEM images we saw before. So, so that being said, to be able to continue a static test effectively, we pretty much had to do a blank run followed by an adsorption run for every experiment, every different material we generated, and that's in the next slide. Before I go to that, so we had one concern to address from this, right? So because we're losing moisture, and in the TGA recording that as a weight loss, and then picking up CO2 be recording as a weight gain, a question kind of rose up is, are we entirely confident that we are picking up CO2 in the sample? So one thing we did do was we sent a sample out to Anton Parr, who used an Autosorb IQ to perform chemisorption tests on the material. And what they did was they ran the sample through their system, and the exiting gases went to a mass spectrometer. And before the mass spectrometer was a cold trap to knock out any moisture, so that anything you're detecting downstream in the mass spectrometer and a TCD, you'll be sure that it's CO2. And in the sample we sent out to them, we definitely did see CO2. So this kind of confirmed what we kind of expected. We just wanted an additional confirmation. This kind of confirmed that, the sample does have CO2 capture activity. It's just the static test with the TGA will be a little bit challenging to interpret the data. Next slide. So this run kind of summarizes the performance for all the for the about 16 samples that we tested in the TGA. So to test these samples, like I mentioned earlier, we had to run a blank run, and then we'll run an actual run. So these results are really just a single cycle of the material. So the original material you made, you run it through the TGA, and you can only do a single cycle. And the reason why we could only do a single cycle has to do with the fact that the sample is very hydrophobic. We could not come up with a good way to add moisture onto the sample that we tested in the first cycle. So we just used the first cycle as a screening step to pick what we believe it would be the best performing sorbent. And so far, the best one was sample 10, which is, you can see in the picture, superimposed against our capture target, which was 2 millimoles per gram of sorbent. That is about 8.8% weight per weight CO2 to sorbent. So sample 10 was really the only one that kind of exceeded our threshold. So we decided to then focus on that sample for additional. Next slide. Next slide again. I think we went back one step. Okay, good. So one thing we tried to do because the static test was not working so well, and we're still trying to construct our bench unit to evaluate the sample, we kind of set up a what I would call a low fidelity test unit. If you want to click the next slide so the picture can slide back in, it's an animated slide. Oh, no, it didn't. Oh, there it is. Okay. So you can see here, this is a very low fidelity sample. And what we did here was we made a larger batch of the material, about 10 to 20 grams. And then we put it in that small vessel through which we will flow a CO2 stream and then measure the CO2 composition during the desorption step in a CO2 analyzer. And what was really interesting and actually very surprising was when we did this test, we saw very high CO2 capacities on the material. So this is a sample 10, and you can see the mass of CO2 that we're getting desorbed by doing the area under the curve for the analyzer, and we're seeing, what corresponds to in the initial cycle almost 40%, and then in subsequent samples about 25%. So this suggests that because our material is a pretty much I would assume a very even distribution between the humic acid and the potassium, this suggests that we have a very high utilization of our potassium, which is a very good thing. So the question now is, can we maintain this performance over multiple cycles going forward? So that's something we're still evaluating, but in the next couple of slides, I would kind of present some of our initial results so far. So next slide. And one more. There. So this is an animated slide, so if you could kind of just click as I explained. So this is just a bench scale test unit, and it kind of shows the different components to it, the data acquisition. We do have a steam generator available in case we wanted to do a steam regeneration. Our reactor is at the top right of the picture. So that kind of shows us a control box data acquisition. Next click. And that shows a steam generator, which I already talked about. So next click, I believe that will be the condenser. Nope, the mass flow controllers for feeding a known composition of CO2. Next slide. And then that's just the condenser. Next one. That's our gas analyzer, which we use to measure the CO2 composition coming out of the unit. And then next slide. So, and then that actually is a reactor. It's a small 1-inch vessel. And what we do is we would load the material in the system. It ends up being a packed bed, and then we'll perform the experiment. So next slide. One more. Okay. So I was gonna. I see I'm a little bit low on time, so I'll try this. But this slide kind of summarizes where we are so far in the bench scale testing. So there are two kind of things to point out. If you recall, I said in the TJ testing, the moisture is a key part of our sorbent performance. So one thing we have to do is to be able to rehumidify the sample. So initially we tried to humidify the sample in situ, that is, load the sample in the bench scale unit and then try to humidify it while it's in the bench scale unit. And the bar graphs at the top are the results of those. You can see it's kind of all over the place. So somehow we're not getting a very good humidification. And this just boils down to the fact that our material is a single-digit microns, right? So it does not behave like a standard fluid bed. So it's a bit of a challenge. You get a lot of channeling. So another thing we tried to do was take the sample out of the bed and then do what we call ex situ humidification. So after every run, we take the sample out, we humidified it in a controlled environment, and we continue the run. So here, our performance definitely did improve compared to the in situ, but it's still not hitting the targets we observed when we did the low fidelity test. So we believe that there is still some things that need to be addressed in the unit. So this is kind of what we're focused on right now, trying to optimize our test system. One thing we're trying to do as we're testing is comparing our performance with TGA results during the desorption step to see if the numbers actually do make sense, just to reduce the sources of error. If you want to go to the next slide. Okay, and this kind of slide kind of tries to detail some of those sources of errors that we've tried to handle. In the two plots in the right, the second and third run, those correspond to runs where we had just a packed bed of material, and then we tried to do an adsorption and desorption. And you can see the plots show a temperature profile in the bed as a function of time. So you can see that there is, we have thermocouples at different points, and the temperatures are they kind of look like roughly the same during the adsorption step. But if you go to the fourth run, you can see that the temperature peaks kind of shift out, similar to a packed bed system. And this is primarily because what we did was we added inert large particles into the bed, like 1-2 millimeters, to kind of help improve the gas distribution during the adsorption and desorption. So that has improved performance, but we're still not, we still believe that there's a lot of unused sample. So we just have to improve how our bench unit is gonna do the adsorption desorption step. Next slide. So this slide kind of summarizes where we are in terms of our initial test metrics, targets rather. So in terms of adsorption capacity, we're doing we've exceeded our target, which is very encouraging. And also in terms of the half-time absorption, we're also doing a lot better than our target. So this is a work in progress. We expect these to change over the last couple of months we have on the project. Next slide. Okay, so this kind of just summarizes the work to date. We've exceeded our initial targets in terms of the capture performance, but we have a lot of work to do on exactly how we're able to test the material in a reliable, high fidelity test unit over multiple cycles, because our target is to try to get 100 cycles done on the same material. So we'll keep working on that. We also plan to do more analysis on the chemisorption to fully understand what is happening on the sample, and then we'll proceed with a techno-economic assessment of the process, a very high level techno-economic assessment of the process. Next slide. Okay, so I'd like to acknowledge obviously the sponsors, DOE, and a private sponsor, North American Coal, that kind of provided a caution for this project. A special thank you to Dr. Hoffman. He's been very instrumental in helping us kind of identify some of the errors or challenges in our experimental setup. So that's been very helpful. Dr. Laird at NETL and Dr. Gerard Govan at North American Coal for supporting us in this project. Then I especially want to thank Belal Abdelmalek. He's a graduate student working on this. He's the one who generated most of the data we've seen here. And Dr. Van der Vat, who also works with me, and Ji Zhang, who's another student who has been helping us, who has been helping with the analysis. He works at the analytical lab where we're doing some analysis. Okay, I think the next slide is just the disclaimer. But, okay, so that's it. That's all we have.
Okay, excuse me. Thank you, Junior and Xiaodong. We'll go on to the next presentation. This is by Theo Tsotis from the University of Southern California. Theo?
Thanks, Bruce. The next 20 minutes or so, I'm going to try to give you a short overview of some of the work we've been doing as part of the UCFER program on trying to use a reactive separation method for CO2 capture from flue gas. Next slide. The talk outline, I will give you a brief introduction, tell you a little bit about our experimental approach, then give you some of our results and conclusions and some of the ongoing future work. Next slide, please. So this is motivation. I know I'm talking to the converted here, so I'm not going to spend lots of time. Our motivation, of course, is trying to separate and capture carbon dioxide, which is a serious problem, mostly produced from the combustion of fossil fuels. And our main effort here is to try to somehow find a way of reduce some of the cost involved in the capture and separation of the carbon dioxide. And our approach has been in terms of trying to produce some useful chemicals, in particular alcohols. In this UCFER project, our main focus is on methanol, but also we're having some ideas and thoughts about how to produce higher alcohols as well. And the process we're studying is not necessarily an unknown process. It's known as the Chimera process that involves 2 steps. The first step is the reverse water gasification step, in which you take the CO2 and produce a syngas, and then you followed by the alcohol synthesis step. And our claim to fame here is that we have developed an effective way of doing the alcohol synthesis step by using a membrane conductor reactor concept that we have been looking at for a little while, and that helps us to overcome some of the severe thermodynamic limitations that the alcohol synthesis process encounters. Next slide, please. This is the slide just summarizing of what I just said about how difficult it is to run the methanol synthesis reactor at the typical conditions, temperature and pressure shown there on the left. The per pass conversion is around 25%, which is not a good thing. That means you have to recycle a great amount of syngas. So next slide, please. So we have worked on developing this novel reactive separation technology, which we named membrane conductor reactor system. And this is a schematic really of our lab scale system at USC. It's typically the reactor is a packed bed, but different in the sense that inside the packed bed, we have a membrane, a high temperature inorganic membrane, through which we flow a sweet liquid that removes, separates in situ the alcohol and the water produced by the reaction in the process, then shifts the thermodynamic equilibrium to the right, but also provides another function, which is being able to remove in situ the exothermicity of the reaction, which is another one of the key challenges the alcohol synthesis faces. Next slide, please. So some of the advantages that this MCR technology offers is higher process synergy, and this results from combining reaction and separation in the same unit. As a result of that, we overcome the thermodynamic equilibrium limitations. Also, as I mentioned, the liquid sweep serves also as an effective coolant for the reaction, therefore provides higher energy efficiency. And as the result of all these advantages, we end up with a more compact and flexible process design. Next slide, please. Key objectives for our UCFER project is to investigate the performance of this integrated process that combines the reverse water gasification reactor and the MCR process for efficient methanol synthesis in this case from waste CO2, and study its performance for a broad range of pressures and temperatures, as much of a broad range one can have in a lab scale system, and then develop models and validate them experimentally and use those models then to figure out the full range of attainable conversions, with the goal here of attaining conversions in the range of 85 to 90%, trying to meet the 90% carbon capture target that DOE has these days. And then hopefully at some point, with the help of NETL, is to provide a high level techno-economic analysis of figuring out how this process compares with the performance of the most conventional CO2 capture and sequestration processes. Next slide, please. And this is the project task and timeline. I was trying to fit the whole thing in one slide. Sure, you will probably be able not to read that, but the idea, it consists of 5 tasks. The first task was just design the lab scale system, then test its individual components. Remember, there's 2 components here of the system, the reverse water receipt component and the alcohol synthesis component, and then test the integrated system, develop models for the components, validate them experimentally, and then use them to do optimization, process optimization, and then eventually, hopefully, a high-level TA. Next slide, please. There is a couple of key elements in the MCR technology, and I've spoken about them last year as well. One, of course, having a reliable, good membrane that you can use. And the key advantage of our membrane conductor reactor technologies versus other membrane reactor type technologies is that we do not require a high quality molecular sieve membrane. What instead we use is off-the-shelf gamma alumina membrane that we get from our industrial collaborators, media and process technology, but we can also purchase the same membrane from several other vendors presently. And what we do then is we take this membrane and we apply our own in-house technology for playing around with the hydrophilic characteristics of the membrane surface to be able to immobilize the liquid sweep within the membrane structure to prevent any bubble through of the gas phase, but without allowing the liquid sweep to penetrate on the other side, and that create a lost solvent source during the process. Next slide, please. The other key component, of course, is selecting the proper sweep liquid. That sweep liquid has to have a number of key functions, has to be provide high solubility for methanol and water, be able to withstand the temperatures, not volatilize, and also have very high decomposition temperature here, and then also high thermal capacity. And we have looked at both organic type solvents and ionic liquids, and I list here the 2 ones that we found to be the best among the 2 categories. And in this particular case, the ionic liquid is really superior to the organic solvent in all these categories that I've listed here. And then you may ask, why do I even consider then the organic solvent? Because the organic solvent presently has another key advantage over the ionic liquid, which is cost. The ionic liquid costs are coming down rapidly, but still remain quite higher than that of the organic solvent. And so organic solvent in our own mind still remains a key consideration, depending on how fast or how slow the cost of ionic liquid will drop. Okay, next slide, please. One consideration with the ionic liquid that the main focus of this UCFER effort is ionic liquid, as some of you know already, are also used for removing the CO2 in post-combustion capture. And of course, that's a good thing there, but it's not necessarily a good thing in this process, because CO2, since this is a CCU process, CO2 is the key reactant providing the carbon for the alcohol. Therefore, we don't want the CO2 to dissolve also in the ionic liquid. And that's where the first thing we do in the screening of ionic liquids is we carry lots of thermodynamic measurements, solubility measurements. As you see there, the CO2, hold and behold, does dissolve strongly into the ionic liquid at room temperature, but as the temperature goes up, the solubility decreases rapidly, and then by the time we hit the methanol synthesis temperature, the CO2 solubility into the ionic liquid is negligible. Of course, the ionic liquid, next slide, please. Next slide. The ionic liquid, and also the organic solvent, has to have the ability to dissolve the methanol as well. And as you see there, this is some additional data we have generated that for methanol and dissolving both the organic and ionic liquid. And as you see, the methanol solubility is quite significant at these conditions relevant to MES. We are currently developing effective thermodynamic models for modeling the solubility of those of the various products of the MES into those 2 liquids, and we will use those models in the reactor, those thermodynamic solubility models in the reactor models I'm going to present later. Next slide, please. So when we run the MCR system, both using the solvent as the TGD, the organic solvent, the ionic liquid, as you see here, we plot the conversion, carbon conversion as a function of the flow rate of the sweep solvent. As you will see, both of those liquids perform very, very well. At the straight line there is the thermodynamic equilibrium, around 45% at these conditions. And as you will see, the conversion of the system employing the ionic liquid is about 70%. Next slide, please. One concern, of course, with the ionic liquid we had was, will it survive stability-wise the MES environment? And we spent quite a bit of time of doing post-mortem analysis using NMR and other techniques. And this slide is supposed to show you that the ionic liquid does really survive the MES environment, which is a very encouraging result. Next slide, please. Next slide. So there's, like I said, there's 5 tasks here. Task 1, I spoke about it in last year. It was basically putting the whole system together. And the system on the right, which is the MCR system, this is a PNID version of the whole system. The system on the right, circle in red, was the MCR system, high pressure MCR system. That was already in place. But then the system on the left, which is the reverse water gas reactor system, was not. So we spent the 6 or 9 months of the first year putting this whole together and coupling them everything together so that they can operate together as the unit. Next slide, please. Next slide. And this is the physical picture of the whole system inside the laboratory hood. Next slide, please. And then the task 2 was the testing of the individual reverse water gas shift and MCR MES subsystems. Next slide, please. For the MES, we use the typical conventional catalyst, alcohol synthesis catalyst, but we discover, of course, as often everybody discovers, that the manufacturers can sell you the catalyst, but they don't have the focused idea what the reaction rates are for this catalyst. So we spent quite a bit of time, since one of the tasks we have here is to be able to do reactor design, escape lab, and TA. We cannot do this in a lab scale unit, so we have to have the appropriate data to carry those things. So we had to develop appropriate global rate expressions for MES, and that's what we spent quite a bit of time doing that. This is on the left is the design equations for the power grid reactor, where we did the kinetic experiments. On the right side is the global rate expressions we utilized. Next slide, please. To show you that the global rate expressions do quite a bit of good fitting in our experimental data. This is an isoconversion plot where we plot the experimental CO2 conversion with the model fitted CO2 conversion. Straight line diagonal shows very good fit. Next slide, please. And here is some of the experimental data of the MCR system, some of the modeling data. There, and as you see, models and experiments do fairly well. It has lots of confidence to utilize those models for further reactor design and scale up. Next slide, please. And this is another set of data where we plot conversion versus the flow rate of the liquid stream. And again, you see good fit data, good fit between data and global rate expressions. Next slide, please. For the reverse water gas shift reaction, we originally got a catalyst from a manufacturer, high temperature shift catalyst, to discover, of course, that will not be appropriate for our use because its upper temperature limit is about 450 degrees centigrade, and that wasn't good enough for what we had in mind. So we developed our own catalyst here. It's an iron copper scission promoted iron copper supported catalyst. We worked together here with Doug Kaufman from NETL to do lots of characterizations of this catalyst, both before and after using it in our reactors. This is just one of our characterization tests using XRD. And we quite satisfied that this catalyst works well. It's quite stable. And next slide, a couple of slides show some of the data. Could you please, next slide. Next slide, please. Here we plot the CO2 conversion data we have generated for this catalyst as a function of temperature. And on the left, we have the conversion on the right, we have the selectivity. And then this is data at lower pressures. And as you see there, the reverse water gaseous catalyst, of course, generates, it has, in addition, of course, as you may expect, every time you mix.
Anyway, okay, thank you.
Hello? Yeah, so every time you mix hydrogen and hello, can you hear me? Yeah. So every time you mix every time you mix hydrogen and CO2, of course, you expect to produce methane as well, which is not necessarily detrimental to the alcohol synthesis steps, but it of course reflects carbon loss. And so we spend lots of time looking at the selectivity of this catalyst. In the literature, there is no data other than atmospheric pressures. And of course, the original design here was to run the alcohol synthesis at high pressure. So we thought that the best idea was to run also the reverse water gas shift reactor at the high pressures. And the data we show here is a 2-bar. And as you see there, the initial selectivity from methanol is for selectivity for reaction was a little bit on the high side, but then as you increase the temperature, you end up with having very little methane. And that was also consistent with the literature. But then the next tests that we've done, next slide, please. When we looked at the impact of pressure on selectivity, we discovered, of course, as we increase the pressure, the selectivity to syngas deteriorated. And that created a sort of a challenge for us because the original design was to have a system where both a reverse water gas shift reactor and the methanol synthesis reactor will be at the same pressure. And of course, the mere fact that this catalyst, effective and stable as it may be, shows deteriorating selectivity at the high pressures, mandated that we will need to rethink the approach of running the reverse water gas shift at lower pressures and then repressurizing the syngas mixture into the methanol synthesis, and has, of course, that sort of dictated that we do some reconfiguring and reevaluation of our lab scale system. But anyway, we're in all honesty, in retrospect, it would have been a much smarter idea for us to run the reverse water gas shift reactor at low pressures and then repressurize the syngas mixture rather than try to do pressurize the CO2 and hydrogen. But that's, of course, Monday morning quarterbacking. But now we know better. Okay, next slide, please. And again, since this is now our own catalyst, we didn't expect anybody to provide us the global rate expressions. We did not find them in the literature. So we have also had to go and also try to derive those global rate expressions as well. The left, again, is the packed bed reactor equations. The only key feature here is basically that we also have to account for external mass transfer limitations because the reverse water gas shift reaction is quite high, quite fast at these conditions. Anyway, next slide, please. As you will see in the next slide, those global rate expressions do a very good job, of course, in fitting the conversion data. And so we feel very comfortable to use them in our reactor models. Next slide, please. Next, then, we tested the proposed integrated process. We had previously, next slide, please. We had previously tested the MCR system under conditions that are typical for alcohol synthesis, which involves a CO content in the syngas, typically 60 to 70%. But that's not how much CO in the syngas you generate for the reverse water gas shift reactor. So we spent quite a bit of time analyzing the performance of the reverse water gas shift reactor. And this figure here, you saw what we call the CF, which is effectively the CO content of the syngas emerging from the reverse water gas shift reactor as a function of the hydrogen to CO2 feed ratio into the reverse water gas shift reactor and the temperature. And then with the knowledge of what kind of composition we would expect. Next slide, please. Next slide, please. We carried both packed bed reactor, but also MCR experiments with the MES, utilizing the feed compositions that one would expect from the reverse water gas shift system. And these are some of the data 3D plots here in the case we for the PBR plot conversion versus temperature and the carbon factor, and the surfaces there are the models themselves that they do a very good job in plotting it. And the next slide, please, next slide. So some of our additional experimental data for various P and CF, and again, the fit of the model. And then next slide, please. Then we're using those data validated models. Then we did some scale up and further optimization of the reverse photogasiv MCR system. And the next 3 or 4 slides. So basically the conversion as a function of the carbon factor and temperature. Next slide, please. Conversion versus carbon factor and the WF, which is the weight of catalyst divided by the feed flow rate. Next slide, please. I'm going to do this fast. I'm running out of time. Yeah.
Yes, if you could wrap up within a minute, that'd be great. Thank you.
And then the next slide is looking at the impact of the sweep flow rate. The next slide, please. And a key component here is I want to mention that important here is to be able to remove the water that's coming out of the reverse water gasiv system, because if you keep the water around, that seriously impacts the performance of the second stage. But from the last 3 slides that I had to speed through, you probably noticed that we can attain conversions approximately 85 to 90% direct alcohol conversion from the syngas, which is basically almost near meeting the 90% carbon capture target of DOE. Next slide, please. And that's the progress today, summarized in that slide. The only thing that remains right now for us, and we're a little bit challenged here, of course, because we're kind of novices, is to be able to do some high-level TA. But I spoke to Krista Hill, and she told me that I can ask for help from NETL. I haven't done that yet because I'm kind of embarrassed yet about our knowledge of how to do TAs. But once I feel a little bit more comfortable, then I'll contact the NETL folks, try to organize something together. Next slide, please. And future work, like I said, continue testing the integrated system and focus our attention on the TA. Next slide, please. Some of the areas we have collaborated with NETL, I already mentioned Doug's name. We have that part has completed, and hopefully we're going to be able to organize something to work together for the TA part of our study. And next slide, please. Just acknowledging some important people, Krista and Doug, of course, from NETL, and of course, Bruce, who's been a great person helping us administratively. Okay, sorry for getting me stuck a little bit longer. Okay, thanks everyone.
Thank you, Theo. What we'll do now is we'll go into the last presentation in this section. It is by it's by Maohong Fan from the University of Wyoming, but I understand there may be a couple of other people, Andrey's Fast and Randy Vanderwall, who might be participating in this. Maohong, do you want to get started? Maohong?
Yeah, can you hear me right now?
Yes.
Okay, thank you. This is a project title, Use of a Novel Process for Revolutionizing CO2 Capture. The research team, including a member from University of Wyoming and Penn State. And also we have a collaborator, Dr. Jenny Steckel. Next page, please. So this is a lab setup at the University of Wyoming. The left side is, it's kind of drawing like a flow chart. The second one is the right side is really the actual lab setup. If you look at the setup, we have 3 parts. Really, it's the first part is like a gas simulation. Gets CO2, gets nitrogen, oxygen, we use a different mass flow controller to simulate the flue gas. The second part, the reactor part, that's reactor. The third part is monitor, which means we use a gas ladder to monitor the concentration of CO2 from outstream. Next page, please. Okay, the first one I show you, we use a 15% piperidine solution, and we use the same amount, same concentration of MEA to make the comparison. By the way, here is 50% by the weight, but the two amine solution actually use the same concentration of nitrogen. Okay, so 5.87. You can see the difference, significant difference between MEA and piperidines. The piperidine can have much longer, 100% CO2 capture time, much longer. Next page, please. This page shows you the loading of the catalyst on the CO2 absorption with piperidines. We checked 0.25 to 2% catalyst concentration. We found 1% is the best number, best concentration of a catalyst for this absorption system. It really is a purple line. If you look at the line figure, it's a purple line, and basically the rightest line on the figure. Next page, please. And we did a desorption also. We saw the effect on sorption, and also we want to see the effect of a catalyst on desorption. You see clearly see this catalyst help desorption also, because the peak value of CO2 desorption rate in terms of millimole per second is higher with the catalyst compared to weight of the catalyst. Next page, please. Okay, here, last two pages we use a 50% piperidine, but we realize most, the reality is around 20%, 30% amine solution. So we use a 20% to see what happens. If you see the 20% solutions, well, for both MEA and the piperidines, basically we use a 20% piperidine, but actually MEA solution may be concentrated a little lower because the molecular weight between piperidine and MEA are different. But we use the same amounts of nitrogen. Really is a more nitrogen concentration. It's a 2.23 millimole per gram. See clearly, you can see MEA cannot reach 100% CO2 capture efficiency for the whole capture process, but piperidine can do it. That is different from a 50%. For 50% MEA, you can get there. You can get 100% capture efficiency, but for 20%, under these conditions, well, actually a little lower for 20% for MEA, piperidine 20%, because again, the molecular weight, of the two amine are different, little different. Okay, so but sure, the piperidine can get very good, 100% capture efficiency for much longer time, but piperidine cannot. Next page, please. Also, we're looking at desorption for piperidine and MEA. You can see desorbed CO2 from a piperidine solution. That's the base. Let's say desorption rate with piperidine solution is much higher, basically double. Peak value double that of MEA-based CO2 capture system. So basically, this guy is the catalyst helps CO2 sorption and the desorption. Next page, please. And also, we did a catalyst concentration for 20% piperidine. We checked 0.2%, 0.4, 0.8%. We found that 0.4 is the best. Actually, it's very proportional to 15% piperidine, because that's when we use 1%. This one we found 0.4. Basically, it's 14% of the catalyst used for 50%. That's proportional. That means the two systems are very really confirm each other. Next page, please. So you can see clearly, you can see the catalyst loading of CO2 desorption effect in this figure. Really you see the peak value of CO2 desorption in terms of millimolar per second with the catalyst, 0.4% catalyst is almost double that of CO2 desorption rate in terms of millimolar per second without the use of catalyst. Next page, please. Here we did change because catalyst we have two components, okay? So we try to manipulate the ratio between two components. We found really has not really significant difference, but we saw the 1-to-1, best, but really it's a little, better than other, 1-to-2 or 2-to-1 with chloride and also basic aluminum formate. Looking at ratio, not significant different, but we choose 1-to-1 ratio between two components, which is a composite catalyst. We call the DES. It's deep eutectic solvent. Next page, please. And also this page show you, the CO2 desorption, CO2 absorption we see in the piperidine solutions is the best in the lower temperature, 13 degrees C compared with other temperature, 14, 15 degrees C, because it gets more CO2 sorbed. You can see both charts, but you see the right chart, you can see that difference significantly. Next page, please. Well, because we can absorb more CO2 and the lower temp at the 13 degrees C, certainly in the same desorption temperature, 85 degrees C, we can dissolve more CO2 also. This is a clear evidence from these figures. The blue peak is much higher than the gray peak, 15 degrees C. Next page, please. And also we changed the CO2 concentration from 5% to 15%. Between 10, 15, between 5, really 43%, you can see the CO2 capture, 100% CO2 capture time, certainly longest with 5% CO2, 15% is much lower. That's really is visible because with the same time, you really add a different CO2 in the solution. Certainly the time is different because we use the same amounts of piperidine, basically NH2 group to solve CO2. So the number should be this should be expected as theoretically. So next page, please. And also we changed the flow rate. Clearly you can see, certainly the higher flow rate you use, the lower the 100% CO2 capture, the time you can get. The really is, we even look at the 500, 1,000, actually the time is very proportional, right? Because the 2,000 seconds for 1,000 milliliter per minute, and about 4,000 for 500 milliliter per minute. However, for 1,500 milliliter per minute, it's really relatively lower because this is a mass transfer kinetic control issue, because you have too much gas flow in, so the solution is not capable to solve those CO2 quickly. That's why you get relatively lower percentage of CO2, 100% CO2 capture time. Next page, please. Yeah, we did check this stability of the piperidine CO2 capture system. It's pretty stable for this cycle. We didn't see significant decrease for this, the CO2 absorption capacity. We did a turnaround. So with that, I think I finished because time is very limited. I finished my talking with universal warming data. I would like to invite my partner from Penn State. Thank you very much. Penn State team, please. Next page.
Thank you. Well, as part of this collaboration, we were tasked with finding and testing the kinetic constant for the absorption of this CO2 in these absorbents. So the way that we started was first by modeling our system as a very simple liquid phase reactor, considering this is batch respect to, continuous respect to the CO2. We made a couple of assumptions to simplify further the model. Can I have the next slide, please? Okay, so we perform our material balances for CO2 and for second components others. Here, the tool that we are intending to develop has two intentions. The first one is to model and to subtract the kinetic constant for the absorption of CO2 on this catalyst, and the second one will be to verify these kinetic constants. So the variable that we are obtaining from our experimental data is we call it phi. It's at the exit of this at the gas exit of this reactor, and that's the fraction of the CO2 that's present at the exit respect to what was entering fed into the system. Next slide, please. So by solving simultaneously these material balances, we can obtain an expression for the number of moles in the liquid as a function of the change that we observed on that experimental variable phi in the exit, and also its time derivative. The total change of for the component 8, in this case, it's what we call the CO2, would be defined as the contribution of we're observing, the total change of A to any of the chemical reactions in which it is participating. So by using the definitions outlined on the previous slide, we now have a expression that will allow us to obtain the extent of the overall reaction as a function of our variable phi. And using that, we can obtain the concentrations at any given time inside of our reactor. Next slide, please. Yeah, so this will be the first part when we model the reaction kinetics. We end up with this very simple differential equation that we write for all our components of that we are considering. Only considering entrance and exits for the CO2, and the other ones just to continue having the balance for the other components. Here, the part that we will feed to our model will be the proposed kinetics expressions that will be given by these two expressions at the very bottom of the page. Next slide, please. We're going to solve these equations using this software. It's very similar to MATCAD for those who have used it before. Next slide, please. Okay, so our first attempt was to use like the simplest version for the kinetics that we could think of. In this case, we'll be expecting that the reaction will have a first order dependence on the concentration of CO2 and first order dependence on the concentration of the amine on the liquid. We just rewrite this expression in terms of the extent of the reaction. Upon integration, we can use this to obtain and predict our kinetic constant. Next slide, please. By introducing this kinetic constant into the specific expression for the rates of the consumption of CO2 component A and amine in component B. We run that, we integrate this over time. We integrate, sorry, the differential equation that we showed on the previous slide over time. And that will give us a result of the predicted extent of the reaction at any point in time, which we can correlate back to the predicted concentration at the exit. So here in the line in back, we see how the experimental data we were originally provided. The orange line will be the result of using this, like the very most simple kinetics observation. Can I have the next slide, please? We did some adjustments. We added the possibility of, I mean, we knew that these reactions were likely to be reversible. So we added an additional term that will contemplate the possibility of having reversible reactions. And when performing the integration under the same exact conditions, can I have the next slide, please? We find that now the experimental results, the predicted results using this reversible interpretation of the model match appropriately the experimental results, at least for the first few minutes, where until the past of the breakthrough time for this 10%, 90%, sorry, removal of CO2. So can I have the next slide, please? Well, what we obtained or learned from this kinetic model is a good prediction of the breakthrough time, a good match during the initial times on the run. We see that as experimental time increase, there are discrepancy in between the experiment and the simulated data. In this case, we're contemplating the possibility that the dominating mechanism of reaction is changing different stages of the reactions. But yeah, we are working applying this into the analysis of the rest of the curves for comparison of different experimental parameters. Yeah, sorry, our collaborators will continue with the next part.
Hello, can everyone hear me?
Yes.
Great. My name is Randy Vanderwall here at Penn State. So our collaboration part in this task was the techno-economic analysis. So we modeled the system for the TEA based on an MEA equivalent system, taking into account some of the advantages of the pyridine system, as aforementioned. Our analysis did not include the kinetics. Those were based on the rate and modeling, but they did not affect the hardware. The TEA is broken down into capture inputs, capital costs, operations and maintenance costs, and then we summarize that to a cost per ton of CO2. Next slide, please. So as these systems go, they operate in a tandem system, a pairwise configuration consisting of first an absorber unit. The CO2-rich flue gas goes in through a countercurrent flow of the absorber, in this case, the pyridine system. There are various heat and mass transfer balances, especially with regards to makeup water and cooling. Those are not illustrated in this diagram. And then, of course, the regeneration unit as well, where the CO2-rich stream concentrated is then subsequently dealt with, along with the regenerated pyridine, then recycled back to the absorber. But in reality, the real system in totality is more complex than this somewhat simplified diagram. Next slide, please.
Hey, Randy, we'll need to wrap this up in the next minute or so.
Okay. So in more complexity, there's not only the pairwise system absorber regeneration, but there's also a caustic absorber unit that's included in the analysis. It's essential to knock out the SOx because the SOx would otherwise form particulate in the absorption system itself. So that is a whole add-on piece in addition to the prior SOx of the power plant itself in additional stages of CO2 compression, both for downstream pipeline and then storage. Next slide, please. So just to run through this rather quickly, but we took into account CO2 production, capture island size, namely the size of the power plant. This was based on a 1 gigawatt scale, auxiliary power, steam, raw, and makeup water. Summary of the capital cost, but the point is it's a 1 gigawatt scale for which these estimates are made. Next slide, please. Next, thank you. So in terms of summary of capital costs, I'll just go through it quickly, but they are substantial. There's a capitalization rate per year that gave us the annual capital cost per year, which is still quite substantial. Next slide, please. And then we took into account detailed operational and maintenance costs. I'll call your attention to two aspects, namely one, the caustic scrubber does add a significant piece to this, but the primary operation and maintenance cost are somewhat built in or at least subtracted from that of the power plant in terms of lost steam generation and or the auxiliary electricity. So the operational cost and maintenance is somewhat withdrawn from the potential capacity of the power plant itself. One could say it's a zero-sum game, but those are the biggest contributions here for the total annual operational maintenance cost. Next slide, please. So basically, taking into account the capital cost, operational maintenance annual, we could reduce this down to a cost per ton of capture, and it's on par with that of the MEA systems at present, but this I'll emphasize is a preliminary analysis. All numbers are preliminary. We have some refinement on these to yet do. Next slide, please. So just in terms of summary, I mentioned the captured cost estimate at present. The efficiency was assumed to be 90%, although as you saw from some of the preceding slides, they are better, but certainly when one scales this through the absorption system, which consists of trays, sprays, and other packing systems, the absorption unit itself is a rather complex interior piece of hardware to model. The use of the piperidine reduced the overall operational maintenance cost due to its better performance than the MEA, and we intend to make use of some of those benefits in the refinement of the TEA model going forward. But nonetheless, the capital cost will remain effectively the same. The hardware is as such as needed for the scale of the power plant. Next slide, please. And so what's next? Well, as I mentioned, refining some of these numbers, but these were based on the other operational designs across the country for about half a dozen plants that are actually storing CO2 presently, using it actually for either geological storage or secondary oil enhanced recovery. Anyway, I'll stop there and for reasons of time. Thank you very much.
Listen, thank you, Maohong, Andres, and Randy. And I want to remind everybody that all the presentations are going to be on the UCFER website. So if there's certain slides, certain tables, certain numbers that you want to see, you'll be able to go onto the website. And then with that, I'll turn this over to Omer. I think he's going to run the Q&A session.
All right, thank you, Bruce. So I'm going to ask for Bradley's presentation to be put back up because we did get a question from Junior shortly after Bradley concluded. And once we get it pulled up, I'll read the question out for the audience. And in the meantime, if anyone has any questions about the latter three presentations, please submit them to the chat box if you are unable to submit them to the question box. Okay, good. We have Bradley's presentation as soon as we can get that pulled up, just in case Bradley needs to cite anything. So Bradley, can you hear us? Okay, great. So are there any thoughts yet on the implications of the acoustic-based heating and or cooling requiremements for a full-scale application?
So it's not very relevant because if we go to my final slide, or the second to last slide, it would be relevant for scaling up to, say, the 4-inch. Yes, there we go. Since we are pivoting our design to be this smaller, compact resonating tube for scaling up, The only heat that's going to be generated will just be confined to that tube, and that can just be either air cooled or water cooled, but it shouldn't be really as big of a problem as it is for our current study.
Okay, thank you very much. And I see someone has a raised hand. Okay, we have Dick Bajura. Could we unmute him? Actually, I think I might be able to do that. There we go. Dick, can you hear us?
Yes. Hi, Bradley. I enjoyed your presentation. Could you talk a little bit more about the full-scale size of this device and how it would operate?
So it's all in preliminary kind of back of the napkin idea phase right now, and I pretty much just have it up here on the slide. We were able to achieve a about 30% reduction in packing height just by using this air coupling, which we wanted to avoid because it's not as efficient as, say, directly transmitting that, from the waveguide to the steel packing. But it turned out to work very well, and we're just expanding on that idea and creating something that's modular that can be easily deployed on already existing systems that have a load increase for some reason, or they're trying to reduce stripping costs, or on new systems to keep capital costs down. But I've been back and forth with MPI on this design. They seem quite confident that we can definitely create something like this for full scale.
Thank you.
Great, thanks, Dick. So I'm not seeing any other questions or comments, so why don't we get that break slide moved up. And to our presenters, thank you very much for dealing with it. There were some technical issues I heard that were going on in the background. Thank you for your patience, and I'm glad you were all able to still present at the end of it. I will ask, just in case there are more questions that come into the chat, I will ask the presenters to remain online until the end of the break, which should be, if my memory serves me correctly, or unless, oh yeah, it'll go to 2:55 p.m. So if you guys could stay on until 2:55 p.m., let's get that slide up to show the next presentation slot. We'll go into our afternoon break, and then just before the end of it, we can do quick mic checks for our next slate of presentations, which will be in the hydrogen fuel production and delivery, emissions quantification, and feasibility of recovering rare earth elements. So let's start our break, and we'll reconvene at 2:55. We'll give it 5 more minutes. Andrey, we've had some issue with other presentations staying within the 20-minute time limit. We'll so just a heads up, when we get close to 3:15, that's when we'll want this presentation to wrap up before going into Carnegie Mellon's. So just to let you know. And okay. We will be controlling the slides, as you know, from our end. So if you do notice a bit of a lag, just be patient, give it a couple seconds. We definitely hear you, and we definitely hit that button to go to the next slide, but it might take a bit.
So I should ask you to demonstrate the next slide.
I'm sorry, cut out at the end there. What was that?
Should I ask you to demonstrate the next slide?
Yes, just say next slide, and then we'll go to the next one. Yep.
Sure.
All right, we'll give it a couple more minutes. Thank you. Is Randy Vanderwall still on? Okay. Hi, Randy, can you hear us?
Yes. Hello, is this Omer?
Yes. So Francis is your student. Will he be on shortly?
I would hope so. I did double check, triple check. He's aware of this. We did a sound check, and thanks very much to Lauren for all her accommodation. Tested this last week, so he had no problem last week. And he is in class, I thought earlier, but I do anticipate him coming.
All right, sounds good. So we just need to get a hold of Albert, and I know you guys are working behind the scenes to do that. So we'll skip his mic check and just jump into the presentation from Princeton for now. So I'll go on mute, and Bruce, I'll let you introduce this next speaker. Thanks.
Thanks, Omer.
Yep.
Okay, it took me a minute here. For some reason, I couldn't get unmuted. Okay, we'll start this presentations here after the break. The first one is in the hydrogen fuel production and delivery area. And the presentation is being given by Andrey Starikovskiy from Princeton University. Whenever you're ready, want to get started?
Thank you very much for your introduction. Yep, I'm ready. So I would like to discuss development of a novel supersonic hybrid non-equilibrium plasma reactor for efficient and tunable co-production of hydrogen and value-added solid carbons. The work was done just jointly by Princeton University team and Sandy National Laboratory team. Next slide, please. The common problem of methane dissociation is in plasma, that we have a lot of different plasmas. Actually, we can change parameters of our plasma from almost full equilibrium conditions in arc discharges and to extremely non-equilibrium conditions like E-beam plasma generation and everything in between. So we can have very hot electrons and spend all the energy for ionization and dissociation of molecules, like in E-beam. And vice versa, we can spend almost all the energy for gas heating. So we can have very high electron temperature and cold gas. We can have a relatively low temperature of electrons and a relatively high temperature of our gas. And it is known that for dissociation, it is much more efficient to have just thermal plasma. Extremely non-equilibrium plasma dissociate methane molecules because of electron impact. And you have to spend about 10 EV for every dissociation event. So it is just very expensive from the point of view of energy. Vice versa, if you have thermal plasma, you are dissociating in thermal way your methane. And after that, what you have recombination of hydrogen, and you have association of carbon atoms. So you have some reverse energy flux from your products to your reagents. And that's why this thermal plasma is just more efficient for dissociation of any molecules. Next slide, please. So our idea was very simple. We would like to initiate some chemical reactions in hot zone near the critical section of supersonic nozzle, where the gas is more or less dense. And after that, fast expansion of the gas in the nozzle immediately bring us to frozen conditions from the chemical point of view. So we are just decreasing the temperature and we are fixing our products. Avoiding any reverse reactions between carbon and hydrogen. So we have some hot zone in the discharge area. And after that, we have very fast expansion of our flow, and we will just freeze our products in the state we would like to have. So we would like to have almost full dissociation of our methane in our discharge. And after that, what we have just quenching of our chemical reaction in expanding supersonic flow. Next slide. It's just an example of what schematics of what we did. So we have a rather small nozzle. Critical section or critical diameter of the nozzle is 1.3 millimeter only. Nozzle exit is much bigger, 3.2 millimeters. So supersonic nozzle was designed for Mach 3, and final conditions were just 120 Kelvin and about 20 torr of gas pressure. And initial pressure was about atmospheric conditions and room temperature conditions. Next slide. That's just what happens when we are just powering our discharge. So at low pressure conditions and no flow conditions, we have almost homogeneous vacuum arc between electrodes, and this arc then just propagates around all the cross section of the nozzle. When we are switching to real conditions, real supersonic flow conditions, we have sonic flow in critical section of our nozzle. So we have fast flow about 500 meters per second in this section. And of course, this very fast flow a little bit decreased the volume of plasma. So what we have more or less complete excitation in the case of low pressure flow of the low pressure gas, and partial discharge, and discharge fills our cross section only by 50% in real supersonic flow conditions. Next slide. This slide shows discharge parameters. So we have a rather high frequency nanosecond periodic discharge. In methane, frequency of the discharge was 120 kilohertz. So time interval between discharges was less than 8 nanoseconds, microseconds, and typical voltage was about 2 kilovolts, and typical average mean power of the discharge about 3 watts. Next slide. We modeled the development of this discharge in supersonic flow from the point of view of discharge, nanosecond pulse discharge. Supersonic flow means almost motionless gas. In nanosecond time scale, a gas has too low velocity for any displacement. So we can just assume that the gas is motionless, and we could take into account all the motion of our electrons, ionization by electron impact, dissociation, of course, attachment of electrons, and photoionization, which in methane is very, very weak, because methane would like to dissociate under the influence of ultraviolet radiation rather than ionize itself. So we have a rather low concentration of initial electrons, which means we have very strong negative streamers propagation and a rather slow propagation of positive streamers. Next slide. It's just demonstration of the difference between two different streamers. From the left, we have negative electrode, and from negative electrode propagates negative streamer. This streamer propagates in the direction of electrons motion, and this streamer does not depend on pre-ionization of the gas in front of the ionization wave. On the opposite, the positive streamer, which propagates from right to left, depend on initial concentration of electrons. And this initial concentration is generated only by photo emission of from the front of ionization wave. So we have some delays in propagation of positive streamer because of a very weak photoionization in methane, and very fast development of negative streamer. But as a result, we have conductive channel between two electrodes, which forms approximately in 20 nanoseconds. Next slide. Yep, and this is just demonstration how our potential propagates through the gap, what we have inside the gap as a result. So we have approximately 1 megawatt per meter of electrical field. After the discharge, close the gap. And typical electron density is 10 to 14 per cubic centimeter. And after that, because we have still electrical field much higher than critical electrical field, we are increasing and increasing and increasing electron density up to the point when we will stop our discharge. Next slide. It is just typical picture of what happens as a result of the discharge development. We have relatively hot kernel of plasma near the axis of our discharge, and the rest is just relatively weak ionization by ionization waves. In a very short time scale, what we have just approximately 100 nanoseconds. We have almost complete dissociation of methane. You can see that methane, as a result of this very fast temperature increase, decreases its concentration approximately 10 times. And what we have hydrogen, H2, and we have just carbon atoms. Next slide. We measured hydrogen production in our supersonic nozzle, and we came to the conclusion that without supersonic flow, if we have subsonic regime, we have rather slow cooling, and we can assume some reverse reactions. In this regime, we have to spend approximately 43 kilowatt-hour per kilogram of hydrogen. So energy for methane dissociation is 1.6 electron volts per molecule. In supersonic regime, when we have very fast quenching of all reverse reactions, and we can assume a very efficient regime of methane dissociation, the hydrogen production cost is 28 kilowatt-hour per kilogram, and energy for methane dissociation is approximately 1 electron volt per molecule. If you will compare this with just hydrogen production from by electrolysis, in electrolysis we have to spend 72 kilowatts-hour per kilogram of hydrogen. So we are 3 times below this limit. Next slide, please. And of course, it is very interesting what we have as a byproduct, solid carbon, which we are producing in the discharge. So one product is hydrogen, and another product is carbon. We just measured particles, what we have as a result of this process. We put a golden plate in front of the supersonic nozzle, and we collected particles, in different carbon particles, and we analyzed the composition of these particles from the point of view of different atoms. So it's obvious from the analysis that what we have namely carbon particles without any admixture of any metals from electrodes, nozzle, everything. So it is carbon particles produced from methane, and we have very different shapes of these particles. The longest one, tube on the top row, has a length about 1 millimeter. So we have different shapes, like balls, like needles, and we have and these particles are built from carbon atoms only. Next slide, please. So it's just demonstration of different shapes of particles, different shapes of different structures of carbon products we can produce in this nozzle as a result of methane dissociation. Next slide. As a conclusion, what we have very efficient production of hydrogen and carbon in this supersonic nozzle discharge. Once again, we are using almost equilibrium arc discharge plasma in supersonic nozzle, Mach 3. And what we have conditions which are, from the point of view of energy, we are 4 times, say 4 times below the production of hydrogen in electrolysis process. And solid carbon is a valuable byproduct which we can use in addition to hydrogen. Thank you for your attention.
Okay, appreciate it, Andrey. So if anyone has any questions, please submit them through either the chat or the question box. I'm not seeing any currently, so we are going to pause for a moment just so that anyone who wants to see the next presentation under emissions quantification can have the time to join the webinar. You know, we don't want to start before they're able to join. So we'll keep on time and we'll begin the next presentation at 3:20 as scheduled. But in the meantime, if anybody has any questions, please submit them to either the chat box or the question box. And if you want to say your question verbally, just raise your hand and we'll unmute you. So in the meantime, just for discussion's sake, Andrey, how have you felt about the NETL collaboration portion, and what I guess could you recap some of the biggest takeaways from that collaboration, if possible, while we wait for some questions here?
We have rather fruitful discussions with the people from NETL and from Sandia Lab. So we have a lot of fruitful collaboration just online, but unfortunately, due to virus, we have very restricted in-person collaboration.
Was there a, refresh my memory, was there an arrangement to have someone actually on site for this particular sub-award?
Probably it is better, of course, to ask Igor Andrew, who is PI for this project, but I'm not sure.
Okay, no worries. All right, so again, if anyone has any specific questions, just submit them through the chat. Andrey, thank you for your presentation. Why don't you just stand by and wait until our next presentation begins for any questions that may come in. Oh, wait, did someone raise their hand? Ah, there we go. Sorry, Dick. You are unmuted. You're free to speak if you're able.
Thank you. I can't access the written word. Andrey,
your mic is coming out a bit quiet. I don't know if it's just me. Andrey, were you able to hear him?
Not yet.
Okay.
How about now?
There we go.
Oh,
yep, that's much better.
Great, thank you. Andrey, I enjoyed your presentation. I'm wondering if you would comment on how you think this system would play out at a larger scale with the technology that you're using.
Okay, so scaling up, of course, is always a problem, definitely for the small nozzles, and it is key issue for this nozzle, because what we would like to have, we would like to have very fast quenching. Fast quenching means for chemical, in chemical time scale, you need to decrease the temperature and pressure in few microseconds. It limits the size of the nozzle. So we cannot just build a nozzle with a size of a couple of meters and expect the same results. It's very clear, and it is just the core of the technology. So what we can do, we can multiply these small nozzles. We can use thousands of these nozzles, and we can generate rather high mass flow. But it requires the same small nozzles, but just we need them. We need many of these nozzles.
I understand that part of it. What can you comment on the concept of collecting the carbon? I know that's sometimes a problem. If you're doing catalysis, you can't separate the carbon from the catalyst.
Yeah, because we have no any solid catalyst. Basically, we are using plasma as a catalyst. So what we have a gas flow, hydrogen flow in our case, some mixture of hydrogen actually and methane, and carbon particles in this flow. So we have gas phase and we have solid phase. They are just very easily separated from each other, just because we have relatively low pressure, low temperature conditions.
Thank you.
We have no solid catalyst. So it's not our problem to collect something from solid surface.
Right.
Okay, thank you, Dick. If there are any more questions from the audience, feel free to submit them or raise your hand. We'll keep an eye on it and unmute you if you would like to articulate it verbally. In the meantime, I think we have about 5 minutes before our next presentation starts. So let's take a quick break for 5 minutes before we head to CMU for the next presentation. Andrey, thank you. Please stand by in case anyone else asks anything. Thanks. Okay, I see a message. Albert, why don't you go ahead and test your mic real quick now that you're on?
Yeah, can you hear me?
Loud and clear, perfect, thank you.
Great.
Francis, I saw that you had joined during Andrey's presentation. If you're able, do you want to do a quick mic check?
Sure. Yeah, can you hear me?
Beautiful, thank you.
Of course.
Okay, Bruce, I think I'm going to go ahead and just introduce these next two, since it's just since there's Q&As between each of these, and I'm doing the Q&A anyway.
Okay, not a problem.
All right, so it's about time to start the next presentation. We are moving on to emissions quantification. The emissions quantification section of our agenda. Presenting is Albert Presto from Carnegie Mellon University. He'll be presenting on quantification of methane emissions from the natural gas gathering system using distributed sensors. Albert, we've tested your mic, you're good to go. You have the floor.
Okay, thank you. So my title has already been read, so I guess we can go to the next slide. So, at the time we wrote this proposal, these were the two objectives that we had. The first was to demonstrate that we could use distributed low-cost sensor networks to quantify temporally varying methane emissions from natural gas gathering infrastructure. And then we wanted to apply this, once we got a sort of working sensor, we wanted to apply this approach to measure emissions from gathering pipelines and pig launchers. And if you hit advance, we'll go to the next slide, please. One thing, we ended up having to sort of get rid of gathering pipelines because our NETL partner found that there weren't any gathering pipelines with large enough leaks that they couldn't even measure them with sort of the high precision equipment. So we weren't going to be, there was nothing for us to measure in that case. So our NETL partners in this project were Natalie Peckney and her group. And since this is a question Omer asked of the previous speaker, I'll take a moment to address it now. I thought in general our collaboration was fruitful. We had some pandemic related difficulties, right? Because they were doing field work and could only send one person out at a time. It sort of limited how much we could try and do things together. But sort of broadly speaking, I've worked with Natalie on and off over many years at this point, and I think in general we've had a fruitful collaboration both in this project and in previous ones. And I know she's somewhat interested in trying to continue some of this work if there's a way to do it in the future. Next slide, please. So the first thing we had to do was characterize some of these sensors, and so I'm going to talk about that first. And that work was recently, part of that work at least, was recently published in Atmospheric Measurement Techniques. And so a lot of this, what I'm going to show over the next few minutes, is taken from that paper. Next slide. So we tested, there are a bunch of different sort of low-cost sensors on the market that claim to be able to measure methane. These sensors use different operating principles. And so our first thing was to test a number of them. And so for the most part, there are metal oxide-based semiconductor sensors, or metal oxide semiconductor-based sensors, and a bunch of those are shown on the left. And then some use photoionization, and they're shown on the right. And so we tested all of these. Some of them are from different manufacturers. Some of them, like the trio in the bottom row of the left box that are all labeled TGS, are from the same manufacturer, but they're sort of different flavors of the same sensor that have different coatings to hopefully gain selectivity in certain cases. Next slide, please. So the first thing we did was test everything in the laboratory just to see if we were able to get response. And so we designed a custom printed circuit board that's shown in the photograph in the bottom right. And we mounted sensors of the various types in triplicate into this board. So there's three of it. So A, B, C, D, E are the different types of sensors, and then there are three of each of those. The placement of them is somewhat randomized, or as randomized as we could make them and still make them fit on the board, so that we didn't have any biases. For instance, if there were issues with manufacturing the board and one end of the board was different than the other, we didn't want to have all of the A's right next to each other. Our setup in the lab was we had a reference analyzer for methane, and we placed everything, because we wanted to be able to adjust temperature, we placed everything inside of a box, and then placed that box inside of a refrigerator, and then there was also a heat mat in there. And so that gave us control over temperature. We did not have active humidity control. We were able to adjust the humidity by changing the temperature to some extent. And this is the chamber we use to do the initial testing of the sensors. Next slide. And so what we saw is that some of the sensors performed well. So I'm plotting here sensor response. This is for one of the metal oxide sensors. So the horizontal axis is the sensor response. The vertical axis is the reference monitor. And we have relatively high concentrations. This is 10 ppm, 20 ppm. So super ambient. Only concentration you would get very close to a relatively big leak. But we can see that this sensor, at least responds. If you advance the slide, some of the sensors did not work at all, right? So this particular sensor, this is a different metal oxide sensor, but it doesn't have any sort of coherent response. So next slide. And so we were actually able to eliminate a bunch of these because for the most part, they were like the case I just showed on the last slide where they didn't respond. And so we came down to basically 3 sensors that sort of had promising responses. One is this one called MQ4, and 2 are these variants of these TGS sensors, the 2600 and the 2611. They're both made by a company called Figaro. And so all of these are metal oxide semiconductors. Next slide. We also were able to, because we tested everything in triplicate, we could look at the inter-unit precision, right? So these are 3 different examples of the Figaro TGS 2600 sensor. And we're just showing the sensor response, and the sensor response in this case is in resistance, so it's in kiloohms. And so they're precise, right? In each case, the correlation coefficient between 2 sensors is unity, right? So the R's are unity. But the slope is not always unity, right? So there's unit to unit variability in the response. So if we look at the slopes, which are the betas, they're sort of, in this particular case, they're sort of 1 plus or minus 15%. If we advance the slide, and this was true for all 3 of the sensor types that worked well. There was high precision, but variability in the response, right? Again, so sort of on this case for the MQ4, it was sort of up to 30% inter-sensor difference. So this suggests we've done these sort of comparisons for other low-cost sensors that we've used for sort of traditional air pollutants like carbon monoxide and ozone. And in those cases, we found that sensor to sensor the responses were similar enough that we could build, one calibration model for a whole batch of sensors. But in this case, the variability from one sensor to another was sufficient that we determined that we probably can't pursue that path, that we need to do an individual calibration for every sensor. Next slide. Okay, so we knew going into this that the sensors would show cross sensitivities. Temperature and humidity are 2 important cross sensitivities in this case, because on a metal oxide sensor, you're sort of detecting the change in conductivity of the semiconductor, and water can get in there. When water is available to the semiconductor, it can change the conductivity or the resistance. And so all of the sensors are sensitive to temperature and humidity, and those sensitivities can be pretty big. So I'm showing here a few different cases. So this is for the MQ4 sensor. So the horizontal axis there is the measured methane concentration. The vertical axis shows the sensor response. And I'm showing 2 different temperatures. So the blue points are essentially 10 degrees C. So our temperature controller was sort of accurate to within 1 degree C. So this is 10 plus or minus 1 C. The orange points are 30 plus or minus 1 degree C, right? So this is sort of a typical ambient range that these sensors might see if we had them outdoors. And so one thing to see is that clearly between 10 degrees and 30 degrees C, there's a big difference in the response. And then if you look within each temperature, there's this sort of periodic up and down. That's essentially the fluctuations in the temperature due to the temperature controller, right? So this is the plus or minus. So you can see sort of the magnitude of the variation we get from the plus or minus 1 degree around the set point from the temperature controller. On the right, I show the same sort of plot, but now we're coloring by humidity. This is absolute humidity, not relative humidity, but you get the same picture if you plot relative humidity. Because we weren't actively controlling the humidity, the changes in the humidity are basically from the fluctuations in the temperature. And we see a similar story, right? Low humidity in green, high humidity in orange, big difference due to humidity, and then those sort of humidity changes that are imposed by the temperature fluctuations, give us sort of a noticeable response in the sensor response, or a noticeable change in the sensor response. Next slide. Okay, but even with those variations, we were able to build sort of workable calibration models. And this is one example from a very simple model. This isn't the best performing model that we produced, but it's the sort of simplest. So I'm showing it as an example here. So now I have the actual methane concentration on the horizontal axis, the inverted concentration in the ppm in the on the vertical axis. And we're going to add a couple reference points here. Because we were sort of starting with room air and then doping the room air with methane, if you advance the slide once, you'll get a vertical line right around 2 ppm. That was the background in the laboratory, right? So we were never able to go below 2 ppm, but the sort of global average methane is about 1.86 ppm, so we really don't need to necessarily worry about situations below that concentration. And then we went up to sort of 10 ppm as sort of a range we might expect to see. As I said, this model was relatively simple. So if you advance the slide one more time, the model form will come up. And so in this case, the predicted, or the concentration is just from a multilinear regression. So we have an intercept term that's alpha, and then we have sensor resistance as one of the explanatory variables. In this case, absolute humidity. And then the third term is a cross term between humidity and sensor resistance, right? So again, a physically simple model that captures, some of what we know are the things the sensor is going to respond to, and it performs reasonably well. This was not the only calibration model that we built. We tested several different types. So advance the slide, please. And then just hit one more. Okay. So we tested a bunch of different models, and I apologize, the type on this slide is a little bit small, but this is for the MQ4 sensors. And the way this plot is organized is that each colored symbol is a different model type that we tried. The horizontal axis is the R² value from that model when we tested it on the data. And this axis is reversed, right? So R², the best R² you can have is unity, is 1. And so we've reversed this axis so that 1 is on the left and 0 is on the right. The vertical axis is a measurement of the mean absolute error. And it's actually the variability of the mean absolute error. And this is something that we want to have small. So the way this plot is organized is that the origin is essentially a bullseye, right? You want to hit the origin because that means you have high correlation and low error. And so then the worst performance would be the top right, because that would be low correlation and high error. And so we can, see that different model types perform differently. And just very briefly, there was a linear model only based on sensor constant, or only based on response, a quadratic model, a couple multilinear models, and then 2 from the literature. Those are the 2 labeled UCFER, the purple star and the gray X. These are from recent papers from that group. So if you hit advance, it'll pop up the same sort of plot for the other sensors. And we see variation. Pardon me for one moment. The hotel staff is coming to clean my room, and I need to tell them I need silence. I'm sorry, very sorry for the interruption.
No worries.
Sorry, I'm away at a conference this week, and so doing this from my hotel room. So as I was saying, we each subplot here is for a different sensor. In general, this UCFER model is the best performing, but we didn't proceed with that one because if you advance one more time, it actually shows the format of that model, and we think it is overfit. There are a lot of terms in there. I'm not going to go into what all the terms are, but we're pretty sure that this model is overfit, and so didn't want to go forward with it. So for the most part, we use the MLRs, black square and the green diamond. And for the most part, they perform similarly. And then one more time on this slide, one more advance. And the one thing we haven't done yet is we've sort of stuck with one model per sensor, but presumably, a model that incorporates multiple sensors might be better equipped to handle some of the cross sensitivities here. Next slide, please. So, we did this testing indoors, but really to get a good range of temperature and RH, what we really need to do, what we've learned before, is you need to do this testing outdoors. So we did that. We actually took all of the sensors and our reference monitor outside and put them under a tent. The tent was just there to protect from rain. But if you advance, we didn't get enough variation in methane. We did a lot of these tests at our campus in Pittsburgh, and there was just no variability. There were no inversions to give us high concentrations at night. There were no local sources. And so, we could measure 2 ppm and predict that, but that's not very interesting. So if you advance again, what we did was then we tried to dope the ambient air with a little bit of methane. So we put a cylinder near the tent and flowed out methane at a controlled rate. EH&S was there to make sure we didn't create explosive conditions. And that gave us some variability. We were able to get occasional spikes. And so then we had sort of natural variations in temperature and humidity, and then sort of these imposed changes in methane. Next slide, please. But in the lab, we were able to account for these changes in temperature and RH, but in the ambient, the temperature and RH changed fast enough that we couldn't, our model wasn't able to keep up with them. The temperature and RH changes would sort of swamp everything. And so then what we moved on to, next slide, please, was to build different models for different bins, right? So we found that that in certain, especially relative humidity ranges, we could get good performance. So these are all the color here. So each column is a different range of relative humidity. So lowest on the left and highest on the right. And then we have entries for each of the 3 sensors in triplicate. And then the color of each box just shows the correlation coefficient between the methane concentration and the sensor response, right? And so, for instance, we get the best performance when it's dry, all the way on the left. But in general, when humidity is stable, and then we can build sort of separate calibrations for different temperature or for different humidity ranges, we get better performance than trying to correct for the humidity in real time or build it into a sort of an overall model that corrected it as we went along. Next slide, please. And so then this is an example for one of the sensors. This is for one of the Figaro sensors. When we subselect, a portion of humidity, I think this is for 14 to 28% relative humidity. We get better performance. We're still over predicting a bit, but this is better performance than when we just tried to sort of incorporate one model that accounted for humidity under all possible humidities. Next slide. And so we were able to then take our sensor package that we had tested sort of both in the laboratory and on our campus, and we took it to a few different pig launchers. I'm showing one here on multiple occasions over the course of varying months. So we had it there in the winter, we had it there in the spring, and in the summer a bit. And there were 2 different pig launchers that we were able to visit. This one in particular is a very large one. So the dashed rectangle shows where the pig launcher is. We were able to park sort of near where the star is. That was a few hundred meters downwind. And the goal was to capture variations in concentration so that we could quantify emissions, right? So what we sort of want is to see a plume of methane that comes by, and we can integrate that plume and use that, use Gaussian dispersion to estimate the methane emissions. Unfortunately, we never sort of saw that event, and we had our reference monitor there too, so we know that this wasn't, just an issue of the sensors not performing well. So if you advance again, right? So we saw the methane was elevated at the pig launcher. So when you're, for those familiar, this is in Washington County, Pennsylvania. You do measure elevated methane in those areas, but we never sort of saw any plumes that would allow for the emission estimation. And we went, as I said, we went to a couple different pig launchers. We went under varying conditions. We're able to detect the elevated methane, but we weren't able to get sort of a plume that would allow us to do this Gaussian dispersion calculation to get the methane emissions. And so that's something we're still sort of chasing after. We have a few more months till our project ends. So then if we go to the last slide. So yeah, sort of what did we learn and what are the next steps? As I said, the correcting for the relative humidity and temperature interferences is something that's hard to do in real time. And so we've had better performance by just sort of binning and trying to focus on times when those variables are not changing so much. In general, the sensors perform best at low relative humidity. This is actually in contrast to some of the published work with these sensors. Other groups only use them when the humidity is high. But this suggests that maybe if we were able to dry the sample, sort of actively dry the sample, we would get sort of better performance. And this is more from the lab, for the lab testing, but our limit of detection is about 0.3 ppm for a 5-minute sample under those dry conditions. And so, we should be able, if there are sort of either transient leaks or we go into places where the concentration is elevated, we should be able to quantify those. Just as I said, when we visited the pig launcher on multiple occasions, we never sort of got the sort of plume that we needed to be able to sort of do the emission estimation that we had hoped to do. And so that is my last slide, and hopefully there are some questions.
Great, thank you, Albert. While we wait for questions to come in through the chat or for individuals to raise their hands, I did have I guess this is a good segue into what I was curious about. If you were to be given, say, another few years and another award, assuming coalition were to be extended, what kind of scope would you deal with? How would you advance what you've done here?
I think definitely this middle bullet point, like trying to put in a dryer would really make these much more robust in terms of their response. Sort of building a prototype that had a dryer in it that was an active dryer, not like just some sorbent bed, because we would have to replace the sorbent bed every day. I think that would be a high priority. And I think, and this is like generally a challenge with the distribution infrastructure is spread out, right? And it's often, like you saw, there's this one big pig launcher and it's, and then several kilometers to the next source. So thinking maybe about ways that we could leverage some of these sensors in a denser way. There are a lot of like urban methane leaks, right? From the residential and commercial distribution system, or from buildings. And so like trying to deploy them in a way and do an inversion framework like at an urban scale or in places, even in suburban areas, there are big methane sources like landfills, and landfills are a big one, where you could sort of target a standing source that you, and then you're less reliant on like the activity at this, for a landfill, you're more reliant on the wind blowing things the right way than like the activity of the pigging happening when you're able to be deployed at the site. So those are things that I would think about targeting.
Okay, and I apologize if I missed this earlier while we wait for some more questions to come in. Have you talked about the potential for industry buy-in or input during this research?
We did not directly connect with industry. I mean, I know in general, there is a lot of sort of industry interest in low-cost sensing for environmental applications. Like that's literally what I just came from at the last session at the conference I'm at, was companies building low-cost particle sensors. The marketplace right now on at least on like the air pollutant side is from like very small startup type things to some of the really big equipment manufacturers are interested in that. And I think, there is also interest on the greenhouse gas end of that as well, though it's less mature.
Gotcha. Okay. Well, I am not seeing any questions come in. If you have any, please submit them to the chat, or if you'd like to verbalize them, please raise your hand and we'll call on you. Albert, thank you very much for your presentation. If you could stand by just for maybe a couple more minutes to see if any other questions come in, that'd be great. Your hotel Wi-Fi is fantastic, by the way.
Yeah, I lucked out, I guess.
Yeah, you did. Okay, perfect. So great, we have the next slide pulled up. Albert, thank you, and we'll get started with the last presentation in a little bit here. I believe we have 3:45. So you know what, we might as well just start now. So the last presentation for today will be under feasibility of recovering rare earth elements. It's by Francis Kuklis from Penn State University, and I believe Randy Vanderwall as well. So I will give you guys the floor. I think we already did a mic check, right?
We did, yes.
Okay, perfect. Well, the floor is yours.
Okay, you can go ahead and skip through this slide, and hopefully my camera and connection will work. I'm outside at Penn State because it's the quietest place I could find. So if it cuts out, I'll cut my camera before we do anything else. Go ahead and go to the next slide. The first couple slides are going to be introductory, so you can skip that. That's just our contact information if anybody wants to have any follow-on questions. This is a thank you note from the Department of Energy funding the study. And this slide and the next slide list all the objectives, but I also have them as the breakup points, so we can just skip them and skip this, and I will read through them as they come up. So the first objective was to identify the industrial opportunity for utilization of REs and recontaining materials within the U.S., and then identify high purity resources domestically for rare earth elements and ensure that they can be utilized to retain domestic availability. Next slide. And so the first thing to think about with this was that for the longest period of time, the United States was not producing any rare earth elements. And we know that rare earth elements is kind of a misnomer. They are, in fact, abundant throughout the planet. It's just that they're in concentrations that are relatively low and not economical to mine whatsoever. Standard, terrestrial soils contain about 0.1 to 0.01% of rare earth elements across the globe. So they are everywhere, but concentrations that are economic for mining need to be about 3% or greater. And so finding those concentrations are relatively rare. Recently in the United States, we have started to develop rare earth material reserves and eventual resources. However, we're still dependent on China for mining those. So we mine, or I'm sorry, for refining those. So we mine them here and then we ship them to China to be reprocessed or put into products and then shipped back to the United States through trade goods. So these charts here, they just show world production by country or by locality over the last couple years for rare earths. And we see that China is the #1 producer. Most of it, about 90% of China's reserves come from northern Mongolia. Australia was the #2, now Burma is now the #2. And the United States has just recently started production at Mountain Pass in California. And our production ramped up in 2018 and 2019. It was a peak. We didn't have the data available at the time for this to continue on into 2021 or 2020, but production has been stable at Mountain Pass as of the last readings. Next slide. So what I did was I kind of took a different approach to this. I'm a geologist by trade, so I like GIS and informational data. So I started perusing through the Bureau of Land Management, any permits for prospecting that have been reported to have positive results, as well as any USGS data for confirmed active mines for rare earth elements. And I've created a Google Earth map that has all of those locations throughout the United States, to include Alaska and Hawaii. And with each of those locations, I then input the data that's the deposit type, which is important to know because for future endeavors, alluvium placers, which is loose sedimentary deposit, would be a lot easier to sift through and mine versus say igneous granites, where it's going to have to be mined up and different sort of infrastructures are going to be needed to put in place for extraction and refining. So I just put the age of the rock for geologic perspective, but the most important thing is, of course, the minerals and the ore minerals that are contained there, because that's what we ultimately want to be looking for. And so I've done this for a majority of the locations for rare earth elements, and I'm planning to expand upon this to do critical minerals as well, just based off of the 2022 commodity summary. And that will be a product that is available with the submittal of our final report. Next slide. So looking at that map, I realize that a lot of rare earth elements are also locked up in non-traditional sources. They're not all just sitting in rocks. So we did a deep dive into the non-traditional sources for rare earth elements, and each of the sources down below at the bottom sort of did a deep dive into one of these aspects that I've listed above. So known coal reserves, coal happens to be quite prolific when it comes to rare earth elements, just the way that sulfates push other things out of coal during the pressuring process when coal beds are being formed. It tends to force a lot of other things out to the sides, mostly above and below the coal seams, but sometimes other elements get trapped up in the coal. So known coal reserves have been proven by the Department of Energy and the NETL to contain significant amounts of rare earth elements, and that that would allow for current coal areas that are undergoing economic devolution or de-evolution to have a resurgence for industrial application. There's already refineries in place. There's already smelters in place. There's already families, generations of coal miners that understand the sort of geomorphology of what it takes to be in a coal mine. So that's something that's economically super impactful if the United States were to further pursue utilizing coal reserves for rare earth extraction. By that same definition, the coal waste itself, whether that's fly ash or tailings piles, leftovers from now dormant coal mines, they contain a lot of the same materials from the push out of those pressurings of coal seams, the parent rock that's around the coal, or just the tailings that were less pure coal that was deemed not to be economically viable for sale, are just left throughout all the mining areas, especially those that have not undergone any sort of environmental cleanup. Red mud, which is a byproduct of producing aluminum, which is something that's not really done in the United States as of today, but it produces a significant amount of titanium oxides as well as rare earth elements as a byproduct, to include iron oxides. So it produces a lot of very useful things and in relatively high concentrations. But again, we're not producing a significant amount of aluminum, so the red mud is not quite as prolific for the United States, but it's still definitely an option, especially as alternative energy sources become available and the possibility of aluminum smelting and production in the United States becomes probable again. Slag and phosphogypsum. So slag is just the waste product from most smelters. We do still do considerable amount of steel production in the United States, and slag is a byproduct of the smelting process. And basically what slag does is in a smelter, it's basically a giant convection tube, and all the heavier things fall out of the bottom, and rare earth elements tend to be heavier than iron and steel. So the slag and the slag glass that gets pulled out of the bottom of the smelters is just absolutely chock full of rare earth elements, titanium oxides. So that's another potential source. Phosphogypsum is a product of phosphorus fertilizer production, and in the Midwest there's mountains of phosphogypsum that are just sitting around, and this phosphogypsum is a hydrate, and it tends to bind to rare earth elements that are left over as a production process, and so those are ripe for the taking. And mine waste sort of kind of goes under the same thing as the coal waste, but mines of different caliber. So the tailings piles, of course, will be a potential source for rare earth elements, as well as any sort of mine waste like runoff. Acid mine drainage is very rich in iron and sulfates, but it also happens to carry some level of rare earth elements. And then wastewater from industrial uses is quite abundant with rare earth elements. And so there's a potential of non-traditional sources for rare earths in addition to mining it directly from the ground, which I'm also attempting to put onto my map as potential sources. Next slide. So the second task was to identify the current industries and specific companies that utilize REEs within the United States, determining the volumes that they need to supply their facilities and where those supply opportunities are located. That last part kind of falls under task 1 still, where the supply of rare earth elements are located, but identifying companies and industries and how much they use is a different matter. Go to the next slide, please. So in some of the future tasks that I'll show here shortly, I was able to identify, based off of industry and companies, the Department of Commerce's sort of breakdown codes for a lot of different things. And I used those codes to populate this, which is the top 10 largest companies that produce in the United States based off of their sales. And I tried to get a small spread of different industries to get a better idea, so I'm not so linear with my predictions, so to speak. So I took the largest company from each grouping that I could find, and then if there was a secondary that had certain reasons to sort of be on this list is what I went with. So I populated the same data for each of these 10 companies just to get an understanding of how much, if possible, they were using or what they were using, so to speak. A lot of companies didn't want to respond to emails or calls, and a lot of companies on their websites, especially their earnings reports, things are hidden behind layers of proprietary knowledge. So some of this is pretty hard to get. But so, for example, I use Tesla, who produces electric vehicles in the United States, and they use a significant amount of rare earths as well as critical minerals. And from their very own website, they say that 90% of what they source comes from Mongolia or China. However, Tesla is currently in talks for critical mineral sourcing, predominantly lithium and cobalt, from Australia, Canada, and Chile. So even with the initiatives for energy independence and switching to renewable energies, U.S. companies, and this was kind of standard across the board, U.S. companies predominantly rely on China for their rare earths and continue to source critical minerals from abroad versus domestically. Next slide. So this map here just kind of shows, and it really closely correlates to the map that I'm producing, whereas mine shows concentrations and availability based off of individual source locations. This just kind of gives a general map of where the REEs are located, which helps answer the question again. But these maps are kind of ever changing, especially lately. There's been a lot of initiative to identify locations for rare earth elements and critical minerals within the United States. So mineral exploration is something that's starting to really ramp up, and so we expect to find more and more reserves. Whether those will turn into actual resources or not is to be determined. Next slide. So the current issue with extraction and refining, just like I mentioned, so there's a lot of push to start being domestic with our productions, but when it comes to refining, you see, based off of this map from the Wilson Center, that China is the powerhouse when it comes to refining. So there's still an incredible bottleneck on the industry of rare earth element production, and that's something that hopefully can be addressed. Mountain Pass is currently building their own processing facility. La Paz in Arizona is another one that's going to be producing their own refining facility, and so hopefully within the next few years we can become less dependent on foreign bodies for this. But the refining process is incredibly energy intensive, and I'll talk a little bit more about that again, but that's a great inhibitor, not just the environmental impacts of refining, but the energy cost for doing refining is severely inhibiting domestic production. Next slide. So now we're going to provide an overview of the global critical mineral resources, their locations, and the processing of resource materials. Next slide. So we're shifting now from rare earths to more to the critical minerals. This is the global distribution of critical minerals, and I know this map is a little hard to read, but it's sourced from the USGS, and it provides basically, if you can sit there and look at the different colors, you can see that within the United States and as well as Canada, we do have significant sources of critical minerals at our disposal, and that we are not utilizing. And it kind of goes hand in hand with hydrocarbons. We have these fantastic reserves. Hydrocarbons, in particular, we are the #1 country in the world for reserves. Some of these other critical minerals, we are also the #1 country in the world for reserves, but we're not actively producing from those reserves. So that's something that we can change as far as international reliance becomes more of a national security issue. Next slide. And this is just another example from the Wilson Center to show, so cobalt is something that we are very dependent on, and Canada mines a little bit. Most of it comes from China. Nickel is something that is found in all sorts of technologies and alloys, and even in catalysts to some degree. Something that is very important for a lot of United States industries. And again, we don't produce any, we rely on it all from domestic sources. And yet we do have cobalt not so much, but there have been found to be some potential reserves in the United States. But nickel in particular, we do have significant reserves, and we're not producing anything domestically. Next slide. So Task 4 provides a historical perspective of all 35 critical minerals produced offshore since 2000, and then also a historical perspective for the quantity of the imports for the United States. I took a slightly different approach on this if you want to go to the next slide. Versus just producing, showing a chart that shows we've produced this much in the rest of the world, and then we've imported X amount. I decided to go based off of imports and domestic production to just show, the disparity between the two, so to speak. So aluminum is kind of my lodestone critical mineral that I utilize for most of these tasks. Aluminum is found in literally everything from from construction materials to airplanes to rocketry and space technology to cell phones. Aluminum and aluminum alloys are utilized in everything, and it's a miracle metal because while it takes a lot of energy to produce aluminum from alumina and previously from bauxite, once aluminum is wrought, it is the only metal that we can recycle without any waste. So you recycle one soda can, you get one soda can back. And so the potential for aluminum recyclability and less dependence on foreign production is there, and I'll talk about that a little bit more. But this chart just goes to show that as far as imports go, and if you go to the next slide, it'll break it down a little further, because you see here the five big players, which I then break apart onto the top chart. And you see that we're importing, barite is pretty much level, and the other three kind of go through small trends, but aluminum is on a slow upward trend. And the data from here, 2019, 2020, we can arguably discount there was this thing that happened in the world that kind of disrupted global supply chains. So that data is not really indicative of an ongoing trend. And I'll show more again about that in a later slide. But the rest of them, nickel, again, we have significant reserves of nickel. We're not mining anything. We have massive amounts of reserves of tin. We're not really mining any, but we're importing. And then the rare earths, that's the story we've already addressed. So there are significant amounts of reserves for each of these in the United States, and for one reason or another, they're just not being tapped and utilized. Next slide. So then we look at the domestic production. Again, this is an overall chart, and some of those are almost, it looks like they're negligible, but each of them do have data points. So if we go to the next slide again, I broke away the top 5 to separate the data so it looks a little more clean. So we see that again, we're producing some things, we're not producing much of others. Some has aluminum again is a perfect example. I mean, we used to produce a decent amount of aluminum in the United States, but smelters are being turned off every year. Land grant policy, mining policy has become less advantageous for new mining exploration, new technologies, and the cost of energy for refining, which is the arguably the key part of production for minerals and metals, is making it less advantageous to do so in the United States. The one exception to that is barite, but barite is predominantly used as an additive for oil and gas mining. for helping with the drills and welling procedures. I would be interesting to see the difference, the difference between why we're producing more if we're mining or we're extracting less hydrocarbons, but that was outside the scope of my study. So next slide. So then we were supposed to identify the top 10 most imported products to the United States that contain critical minerals. And this is where those Department of Commerce HTS codes come into play. Next slide. So I just wanted to get a visualization of the entire market and basically, everything that we import by country. So I was able to find this website, OEC World, that helped populate this data for me. They pull it directly from the Department of Commerce. And basically what this shows is a visualization of all the United States imports. The left side of the chart is color broken down by technology set or industry sector, so to speak. The right side shows it by country. And so what we can see from this, just off the bat, is that almost 20% of all of our imports come directly from China. China, Mexico, Canada are the three largest. And of those, we'll see some breakdown of where each of these come into play. Next slide. So then just using the 4-digit ID codes, just showing the import value over the last 5 years for each of those sectors here. And then if we go to the next slide, I broke it down a little bit further by individual product to see an idea of what the value is of what we're importing. Next slide. Thanks. So from those codes and from that visual graph, I took the actual products from those brackets. I was able to glean the import value of those products. Now, this is for 2020, not 2021, so there's a small disparity in the data, but that's just what was available to me. And then an example of the critical mineral contents that each of those imported products contains, and then the main supplier of those products themselves. And we see consistently that China is a large player, especially when it comes to things like technology and vehicles. Things along integrated circuits are a little bit different, but still, a lot of it is coming from the same places. Next slide. So with task 6 and 7, we're identifying the resource location and quantity of the 35 minerals. I've kind of already done that, and talking about whether they're domestic exports, product reliance, end product, global supply chains. This was a pretty convoluted task. If we can go to the next slide. So what I did was I basically looked at the critical mineral list as of its current state, which is the 2022 critical commodity summary, and looked at each of the materials and seeing how we're importing it, what we're producing. And what we see here is that there is almost all of the critical minerals are in a severe state as far as our reliance on other places. Aluminum is one exception because we do refine, but we don't really produce. So that's why I have it listed as minimal. Beryllium, magnesium, and zinc, we do produce significant amounts, but we also still import. I'm sorry? Oh, okay. Did you say that I ran out of time?
No, you're okay. I think Randy was accidentally he was accidentally unmuted. There's just something going on in the background. So
I'll wrap up quick because I do see I'm a little over. So my basis for that was if we produce at least 50% more of the total. So everything else, the stages are sort of independent, but the critical aspect of that is that most of them are not being produced at all within the United States. Next slide. So then task 7, I'll just pump through this real quick. If you go to the next slide, basically, again, I used aluminum as my most important one. So we see that our consumption is higher than our exports, but we have exports and yet we don't produce any. So it's a very interesting story with aluminum. And basically what happens with aluminum is we import a lot of products that contain aluminum. If you want to go to the next slide, I'm going to use soda cans in particular as the story here. So soda cans are imported and they are the container for a product, so they don't necessarily count as a product themselves, the containers. we import, say, Coca-Cola from Mexico, and the container is just, the vessel in which it's transported, and we're not actually buying that aluminum can directly. So it's almost a free source of aluminum, but because of the way that we have recycling in the United States, only about 45% of all of our aluminum that we import is actually properly recycled. And there's a very interesting case that showed the 10 states that have monetary incentivization for recycling see about a 90 to 95% return on their recycling, whereas the other 40 states see somewhere around 33 to 37% recycling. So in particular with aluminum, a federal recycling program could indirectly make us independent of buying raw aluminum, because we could recycle it for our own needs. And the next slide will show a little bit more on that, because we're talking about it in terms of automobiles instead of aluminum cans. So here we have the end of life for a vehicle. A vehicle gets crunched up into a shredder, and most of the material then gets as a single mass gets sold to somebody else to reprocess, to strip it down, to refine it, and then those individual products then get sent off to a third party, who then buy the scrap, essentially turn it into products, and then ship it back to the United States. That product, the raw scrap material, is called Zorba, and we sell 70% of our Zorba to foreign countries, and 30% of it is used in the United States, but that number also gets broken down a little bit, because there's some that gets directly added to the landfills because of one reason or another. But most of our aluminum that we use in the United States, even if we're recycling it, ends up being sold to somebody else, who then cleans it up, produces a product, sells it back to us. And so we're operating at a continual loss for aluminum specifically. If we can go to the next slide, I know I'm kind of crunched for time now. So basically what I want to continue to do with the remainder of our time, the next few months, I'm going to continue working on my map that will be the finalized product, again, containing all of the critical mineral and rare earth element sources within the United States, investigate the domestic abilities and capabilities for production as slide, and as best as I can really narrow down supply chain convolution, and hopefully build ways to reduce the supply chain complexity, and then identify the highest potentials for domestic production or refinement in terms to both rare earth elements and critical minerals. Thanks for listening. Sorry I talk a little fast. I had a lot to go through.
Yeah, no worries. That was a great presentation. And Randy, I apologize if you had intended to say something during Francis's presentation. Is there anything you'd like to add?
Only thank you very much, Francis, for your excellent work and comprehensive summary in a relatively short time since you've come on the project. Kudos to you.
Of course, my pleasure.
Absolutely. So I think we do have some folks from REE on the NETL side. I'm not intending to call them out or anything or put them on the spot, but we will allocate some time for discussion if anyone has any questions. Okay. Okay. It does not appear it appears that we don't have any. I just have a quick question for you, Francis. I mean, you talked earlier a lot about aluminum, and I was wondering what I apologize if I missed this completely, but I was wondering what your knowledge is of how far along we are with mining aluminum from landfills that were not aluminum cans and materials that were not recycled. Is there any promise there, or?
I'm not sure about on aluminum, but I know for copper, some of the largest new and up and coming copper mines are actually old defunct landfills, because it's copper, it's already in its purest form, and all you have to do is dig it up. Aluminum, I'm not sure. I'd have to get back to you on that one as far as from landfills, but I do know that aluminum can also be as much as 50% of e-waste, and so there are significant places, particularly in East and South Africa, that buy scrap e-waste and extract it from there, which I guess you could call that a landfill. But the potential of recycling aluminum from any capacity, I think, is something that should be pursued, because again, it's tensile strength is 6 times greater than steel. That's why we use it for like planes and stuff like that. It's also actually more conductive than copper. So as far as renewable energy and electrification, if we want to take real steps towards that, I think that the first step is overhauling our electrical grid and removing copper wires and replacing them with high tensile aluminum. So any sort of aluminum sourcing, that we can find that's non-traditional, and especially if the aluminum is already in its metallic state and not as a bauxite or alumina, is definitely worth investigating.
All right, thank you. So I still want to open the floor in case anyone wants to raise their hand. If you do, we'll unmute you real quick so you can speak, or you can send your question to the chat. I'm just going to give some remarks really quick while we wait for possible questions. So to the presenters who are still on, thank you so much for all of your time and for putting these presentations together. I understand that, I apologize that we had to rush everybody, but it was really the only way we could fit all presentations into one session. We didn't want to drag this on to a second day. So we appreciate you sticking to the time limit to the best of your ability. Again, great research. We're in the home stretch here, so we're really starting to get the last good deliverables out of all of these projects. So this is a very critical time, between now and when the last project ends, which is, I think, Bruce, in February, maybe January, February timeframe. And then after that, it's just going to be, compiling all of the accomplishments and packaging it into a good final report. So to the presenters who are still on, I want to emphasize something that Bruce mentioned during his State of the Coalition presentation in the beginning. We're trying to field as much feedback as possible on, the collaborations, the collaboration results that came out of this, any success stories that you have, be it, getting your PhD as a result of the research, or, being recognized in any capacity. We'd love to hear about it, and we'd love to collect that information. So to the presenters who are still on, please bear that in mind. Keep an eye on your emails when Penn State sends them out. Please try to be as responsive as you can to any questions we have about about the benefits of the research and the fruitfulness that came out of it. That's something we want to capture at the end. So, Francis, I'm not seeing any raised hands or any submissions to the chat. All of this is being recorded, though. So if anyone, we will make all of this available in the coming weeks. It depends on how long it takes to process everything. But once we do, we'll send it out, or it will be made publicly available for your reference. You can go back and listen to any presentation you want. And then I believe all of the contact information is available for all the PIs as well. So you can feel free to contact them if you want to copy us. That's great. But other than that, I don't have any more closing remarks. I will pass it off to Bruce if he wants to say anything to whoever's still on.
Yes, I would. Thank you, Omer. And you're correct. The round 6 projects are ending February 1st. I also want to thank all of today's participants. My closing comments could probably be more titled acknowledgements, because this is the last technical review meeting, and the acknowledgements in my presentation were pretty generic. I wanted to put together more of a detailed acknowledgement just because there have been many people involved with this program. And so I wanted to properly acknowledge those that were associated, with UCFER in these various capacities. And this is going to be posted on our website. May change it from the title from closing comments though, but it'll be posted with the other presentations. Next slide. First and foremost, I also want to acknowledge the team that pulled this or put this meeting together and pulled this off. You can see, and it's very similar to Omer's his presentation this morning. The NETL folks, and then the couple people from Penn State. This group was wonderful in pulling this off, and there was a lot going on behind the scenes, even during these presentations, you know, scrambling to get some things done. Because, for example, we found out that one of the presentations had a team, and we found this out just a few minutes before, a team of presenters. We found this out just a few minutes before their presentation, but it all was pulled off without a hitch. Next slide. And then of course, you know, the speakers, and we will modify this one because we didn't know Maohong Fan also had 2 other presenters, and so we'll modify this before it gets posted. But yeah, we want to thank you for, you know, for all your hard work in putting together your presentations and presenting them today. Next slide, please. Now, this is a tough one. This is definitely not all inclusive. There are so many people to acknowledge individually. The people on this slide that are named are those that we've worked with often, sometimes several times a week. But every project had 1 or 2 people, NETL folks associated with it. And so, you know, and then there were folks behind the scenes providing the funding for UCFER. And so, Omer, what I would like to ask you is if there's names that should be added that I may have missed, please let us know, and we'll modify this. But there have been a lot of people at NETL that made this project happen. Next slide. And I want to acknowledge the leaders from, you know, the founding member universities putting together this proposal. Back in 2015, it was quite a massive undertaking, and there were a lot of people from these different universities who were involved. Next slide. And then, of course, the research participants from all the universities. You know, 42 projects to date, over 250 people involved. And so, you know, this was a very large overall program. And again, can't list everybody, but a lot of the key names are on their final reports and even in their acknowledgement sections. Next slide. And just in the running of UCFER, the executive committee that I had listed in one of the earlier slides consisted of 5 people. There were, you know, 3 were permanent. Those are, you know, the top 3: the director, DOE's technical director, DOE's project officer, and then it also consisted of 2 technical advisory committee council members that were elected by the other TAC members. And this is a list of the folks that were, and they were elected for 2-year terms. And, you know, somebody does some math, you probably figure out there's probably more here than you would think. And that's because there were retirements or people leaving UCFER. But we want to acknowledge all the executive committee's help. Next slide. This is the TAC representation throughout the program for each of the universities. And, you know, in some cases, the person was a TAC representative from the onset of the project to its ending. Some cases there was some turnover. And I would like to point out, if anybody from one of the universities notices that we had made a mistake, please let us know. We will correct it. Although Elizabeth double-checked my list and she makes very few mistakes. Next slide, please. And similarly, this is the list of the representatives from each university for the Core Competency Advisory Board. This board and the previous slide, 1 person from each university served on these 2 different, I'll call them committees. And next slide. And last but not least, I want to acknowledge the folks from Penn State. Those in red, those are the current people on the project, part of the operations management team. But there's a lot of other Penn State personnel. I mean, I did not include Penn State leadership who assisted with aligning up universities during the time of the proposal preparation stage. And there are people on here like Jennifer Lear. She's director of our college's grants and contracts. We have people from our office of sponsored programs. They're the ones who prepared all the subcontracts for the projects and did the negotiations. And oh yeah, and also we have somebody who assisted from the Office of Technology Management. So some of the folks in red, we had some part of our we were on the project for some level. All the others here were just you know, the behind the scenes folks. And with that, that concludes, I'll call it my extended acknowledgement section. If somebody has some questions, I'd be happy to answer them.
Great, thank you, Bruce. So appreciate the slides. I want to, let's see, it is 4:25. So what I'm going to do now, I think we'll adjourn the meeting, and if OMT and NETL support could stay on for a quick debrief, that would be great. But again, echoing a lot of Bruce's acknowledgements, thank you all so much for all the work you have done to make Coalition possible to this day. Please finish strong in your research, and please send us all of the accomplishments you can. We want to capture everything you've been able to do. So with that, I'm going to go ahead and adjourn the meeting for everybody aside from the support, and have a good rest of the day. Enjoy the week. Thank you.